Cool. Yeah. Thank you for accommodating me because it turns out my flight leaves on Friday. So since I won't be here, just to like kind of coalesce lectures, I'm gonna give just longer lectures. But if there's no desire for that, we can always just keep it short. Um, but why don't we kind of pick up where we left off last time? So kind of at your behest, I've kind of returned to spinor helicity, and my goal here is to kind of review the derivation of the uniqueness of three particle scattering. Okay, it's just a nice kind of cool thing to see. We're after this going to jump to 4-point. Okay, we're going to do kind of our first leading non-trivial example where there's actually exchanged particles, and still learn a couple more relatively deep things about how rigid the theories that we see in nature are. In particular, the fact that gauge theory and gravity is really rigid. Okay, you can't like easily deform them in a continuous way. Um, After that, I think probably I'll pivot into double copy-ish discussion, just because it's kind of a nice segue, because we'll have presented the four particle scattering, but we'll kind of see where that goes. Okay, good. So where did we leave off last time? So last time we defined so-called spinor helicity variables. The essence of spinor helicity was simply that we write all momenta, four momenta, in 4 dimensions as the product of two spinors, so lambda, alpha, and alpha dot. Okay, so we like take the square root of momenta as our fundamental variables, and kind of miraculously, we will see that expressions just look nice when we compute with them. Okay. Um, maybe I should refine like why the miracle shows up. Okay, like why in the end we're going to find lots of simple expressions. The ultimate reason is that I will never make use of the words polarization. You kind of notice I didn't write E here. I just wrote P. Of course, we know how to write polarizations in terms of spinor helicity. So you could take some classic Feynman diagram calculation from your favorite textbook, plug in for P in terms of lambdas, plug in for polarizations in terms of lambdas. There's formulas for that. You can see my TASI lectures for more details on that, and then just get expressions and simplify them. But as it turns out, it'll be nicer and more convenient to just sidestep any notion of polarizations and that redundancy completely and just build the amplitude directly from the principles of Lorentz invariance and this little group property that I mentioned before. Let me review it again in case you forgot. The statement of the little group says that if you take a spinor lambda and you take its tilde partner and you rescale them oppositely, okay, so this is rescaling by TI, rescaling by TI inverse, then the amplitudes rescale also in a homogeneous way. So like the t's factor out. Okay, so what that means is every single term has to have the same numbers of angle minus square brackets. Okay. Furthermore, the homogeneity power tells you the helicity of that state. This follows from the definition of the little group, which is how unitaries act on irreducible representations of the Lorentz group. Let me not get into why this is true, but this is hopefully a fact that you know. So with these facts, we're now going to go do the 3-particle amplitude, which we started last time, and I'll again pick up where we left off last time, which was the realization that 3-particle kinematics told us that one of the following things is true. Either lambda 1, lambda 2, and lambda 3 are pointing in the same direction, that is to say proportional to each other, or lambda 1 tilde is proportional to lambda 2 tilde is proportional to lambda 3 tilde. Okay. Now, in this case, when these are parallel to each other, then angle 1, 2, angle 2, 3, and angle 3, 1 are all vanishing. Okay, so if these are vanishing, the amplitude can't depend on them. So that's great. That means the amplitude only depends on square brackets. Okay, we like halved the complexity of our ansatz. On the other hand, in this case, the square brackets all vanish. 1, 2 equals 2, 3 equals 3, 1. Sorry. Which means that A has to be a function of the angle brackets. Okay, so what have we learned? There's only 2 options. There's only 2 ansatzes we can write down, which are either A depends on square brackets only or A depends on angle brackets only. Okay, any questions about that? Okay, so we have a bifurcation between 2 choices. Now we just write down an ansatz, as I've said. Okay, so what is an ansatz here? So let's write down an ansatz for the 3-particle amplitude. I'll be a little more explicit with its labels. Okay, so in fact, Let me call the helicity of like one H1, H2, H3. Okay, these are the helicity labels. So again, just so to remind you of my notation, the large numbers 1, 2, 3, 4, those are just like the external legs. So that's an n particle amplitude. And the superscripts, H1, H2, and so on, are the helicities, which are either plus or minus 1. Okay, so let's write down an ansatz, and I got to choose a branch. So let me choose a branch. Let me choose angle brackets. Okay, well, it's going to depend on angle 1, 2, or angle 2, 3, or angle 3, 4, 3, 1, two powers. Okay, I'm going to call those powers N3, N1, and N2. Okay, so this is a rational. Ansatz, as in it's polynomials in these angle brackets. You could immediately ask, wait a minute, there's a lot of functions I can write, like a logarithm, okay, or any kind of strange power. The crucial reason why we're going to have to write powers is because it has to have a homogeneity property under rescaling of lambda. Okay, so if you just wrote some random thing like log angle 1, 2, okay, log angle 1, 2, then under this rescaling, it would the argument of the log would get a multiplicative factor, and then it would shift. Okay, you would get an overall factor of t. Okay, so the functions that have this property are polynomials in these variables. Okay, and that's what you need to be homogeneous in rescaling. So this is our ansatz. Okay, now the key point is we don't know what n1, n2, and n3 are, but they're fixed by the helicities because of that rescaling property. In other words, when I rescale 1, okay, I imagine rescaling lambda 1, then what I find is powers of t, that t1 that go as n3 and n2, and I know that must be pinned to the helicity of 1. Okay, so said another way, let's say I just do this little group transformation on leg 1, then I know that I should have minus 2h1, okay, the power of t1 that comes out, which is minus 2h1, needs to be the number of powers of angle brackets of 1, okay, which here is n2 plus n3. Okay, and so n2 here and n3. Okay. And similarly, we can do the same for h2 and for h3. And we have n3 plus n1, and we have n1 plus n2. Okay, so just we apply the little group across the board. This, by the way, is a very nice way to check like consistency. You know, like we often talk about dimensional analysis as like the leading way of checking whether your answer makes sense. Like make sure all your terms are right dimensional analysis. In scattering amplitudes, you could have 5 terms contributing to something, and they better have the same little group scaling. Okay, even if you didn't know what the external states are. If their little group scaling is different, then it's inconsistent. The whole object is not homogeneous under the little group. Okay, so that's also a good check. It's if you like the rephasing or rescaling instead of rescaling a mass dimension, you're rescaling spin essentially because it's related to helicity. Okay, any questions about that? Okay, now these are 3 equations. We can solve them. N1, N2, N3 can be solved for in terms of H1, H2, and H3, which gives us a formula for them, N1, N2, N3, just functions of H1, H2, and H3, cyclically related to each other. Okay, so now the point here, okay, let me not keep having to plug in these expressions over and over. We have solved for the amplitude in terms of the external data. H1, H2, and H3 are things that you must fix. So those are, of course, a choice you make. I pick some helicities. It could be minus 1, minus 1, minus 1, or minus 70, plus 24. It doesn't matter. Pick some helicities. Those immediately fix these powers. Okay? So the statement is, whatever helicity choice you fix, you have now dictated this structure entirely. Okay? All right, now you can obviously do the same thing for the square bracket case. Okay, so let me not just rewrite the same equations with square brackets, but you can see in your imagination, if I just had changed these to all square brackets, it would basically be the same except but I have some signs here because the helicities flip the other way. Okay, now you might ask, wait a minute, it seems like there's 2 different ansatzes we could have. I could have some choice of helicities. Which one is it, angle or square? Like there's 2 choices. Okay. Well, here's where we keep in mind that there is another important feature of the 3-point amplitude that requires it to be consistent, which is that it better not be a negative power of momentum. Okay, so this had to do with something we said before about having a locality or not having like spurious singularities in functions. A three-particle amplitude should be something that's regular when p goes to 0 and shouldn't like blow up. Okay, when something blows up when you go to special kinematic regions, when it goes to infinity, it means something's exchanged. Nothing can be exchanged in three particles, which means that we have some constraint that the total number of momenta here needs to be a positive power. Okay? So, particularly if I compute the dimension of A1, A2, A3, this thing I just wrote down here, this three-particle amplitude. So this is me computing its mass dimension. It's n1 plus n2 plus n3, right? Because any bracket has mass dimension 1. Okay. Right, that's clear because momentum is two brackets. It's two spinors. So when two spinors contract, it has linear power and mass dimension. So each one comes with 1, and 1 plus n2 plus n3. And this is also known as minus h1 plus h2 plus h3, which let me define to be minus h, which is the total helicity. Okay, I'm defining h to be the sum of all the helicities. Okay, and we don't want this to be negative, so this is non-negative. Okay. If it was negative, then we'd have inverse powers. So in other words, like if we took all the momentum to be small, this thing would go to infinity. Doesn't make any sense. Okay, so what this set tells us is that depending on your helicities, you should use either angle brackets or square brackets. Okay. In particular, if you use the square brackets, everything flips sign. So the square bracket has precisely the opposite dimension, so it has positive dimension precisely when the angle brackets have negative dimension. Okay, they're flipped, they're mirror images of each other, which means that we now have a formula for any three-particle amplitude. So let me write it once, and then okay. So irrespective of any helicity, it breaks into two classes: H2, 3H3. Depending on whether h is greater than or equal to 0 or less than or equal to 0. And let me write the top one once and then never write it again. So angle 1, 2, angle 2, 3, h1 minus h2 minus h3. Sorry. Okay, so that's in the case where h is greater than or equal to, less than or equal to 0. And then when h is greater than or equal to 0, it's made of square brackets. Square 1, 2, square 2, 3, square 3, 1, with similar factors. Okay, let me not just keep writing things. You want to see the exact explicit functions, just go to my TASI notes, and then you can copy them from there. What's the real ultimate big picture, though? The big picture is, if I tell you I have three particles that are massless, massless was crucial because we use spinor helicity, and they couple through a three-particle vertex, then the amplitude is fixed, uniquely up to its overall normalization, the coupling constant. Of course, we'll never fix the coupling constant because that's a parameter that we measure, and unless you have principles to fix that coupling constant, which occasionally happens, coupling constants can be related, it should be thought of as a priori free. Okay? This formula applies, of course, to any spin, like h1, h2, h3 is arbitrary. Okay, so we can take all of them to be 0, and if you just, it's obvious, if all the h's are 0, these are all 1s. Okay, both branches are 1s, which is just saying it's a constant. We already saw that before. We could take h to be small, big, or whatever. Let's look at the simplest cases that we studied, which was the vector case. Right, so the scalar case is pretty trivial. The vector case is slightly more interesting. And of course, we already did that in general dimensions. So we're just going to be essentially computing expressions we've computed before, but seeing how they look when we reduce to 4 dimensions. So for instance, let's consider spin 1, okay, which would be all helicity 1. So that means the helicities are either +1 or -1. Okay, so these would be gauge bosons, vectors, gluons, massless things that have spin 1. Let's consider this. Okay, so it's a simple formula because we just plug in -1, -1, and +1. And then we get the following expression. Okay. Okay, which is a very famous formula for the three-particle amplitude in Yang-Mills theory. So indeed, if you took our expressions from before, we computed with polarizations, plugged in terms of spin helicity, this is the expression you get. Okay, so we've bootstrapped it. The prefactor we don't know a priori, but now we have realized that we should be identifying this with the structure constant. Okay, but this is fixed entirely by Lorentz invariance in 40, just like in general dimension. Okay. For the other helicity, a 1 plus 2 plus 3 minus, it's exactly the same except it's square brackets. Okay, so it should be clear, sending plus to minus, taking the conjugates of these fields just sends angle brackets to square brackets. Okay. Good. Now there's other, so this is it. There's not like a second choice here. Okay. Now you might think, wait a minute, what's going on? For Yang-Mills theory, there were two separate choices we could have for three-particle amplitudes. Where did the second one go? Well, this one here is the minimal Yang-Mills. This is the Yang-Mills three-point coupling. This is the one we know and love. Okay. The one that's naively missing here is the F cubed. Okay. What's interesting about helicity is this is all correct. There's no issue. It turns out that F cubed doesn't contribute to this helicity structure. It contributes to a different one. So in particular, we look at 1 minus, 2 minus, 3 minus. Okay, so just plug in minus 1, minus 1, minus 1. Very symmetrical combination. You get 1, 2, 2, 3, 3, 1. Okay, which is order p, 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 which is p cubed, which is exactly the f to the cubed structure. Okay, so in other words, this is another very slick rewriting of that product of linearized field strengths I wrote, like F1, F2, F3, that thing I wrote a while ago. This is the same thing. Okay, it's also beautifully antisymmetric, and as we know, should come with this. Now that we know what structure it should be. Okay. So and so on. So of course this is a 1 plus, 2 plus, 3 plus, same thing but with square brackets, and these things are the F cubed operator in Yang-Mills theory. Okay. Questions about that? Yes. That's an excellent point. So a priori at this level, no, it doesn't. Okay. And why is that not puzzling? Okay. If I gave you one, let's take this guy and this guy. Okay. This one and this one. Why are these two f's the same? Well, if I just handed you two three-point amplitudes and I said compute one for minus minus plus and compute the other for minus minus minus, I never told you those were the same gluon. Maybe this is hidden QCD, and maybe this is our sector, and maybe this is the dark sector under Z2. It's just different. Like I literally never told you these are the same gluons, so there's no reason these should be the same. It tells you precisely what will make them the same, though. The way to connect the structure constants is to realize that these two things can connect through a gluon, the very same gluon, which is why higher point is what's going to fix them to each other. So you have to look at higher point to dictate that these f's are the same. Yeah, but in general, this would be f, f prime, f double prime, and so on. Similarly, you can imagine a very bizarre setup where these are actually not even related. These aren't real. So minus, minus, plus, and plus, plus, minus are different. Okay. In certain cases, that relates to CP asymmetry, like having CP violating phases. But in other cases, it's simply not even allowed. Okay. So it depends on the circumstance. Okay. Any other questions? Okay. So this is Yang-Mills, and we've derived yet again that its three-particle interactions are unique. And again, I kind of maybe intimated this, but it may seem very, we're focusing a lot on three-point. Like, wow, so much on three-point. Three-point's so easy, it's so unique, why do we care? The upshot will be that from three-point, everything else is free. Okay, that's actually going to be one of the conclusions a little later in this lecture. 4-point and 5-point is trivially abstracted from three-point. So all these statements will ultimately flow into the uniqueness of the entire S matrix. At any endpoint, okay, at tree level, okay. Okay, any questions? Yes, yeah. They don't have to be invariant because only squared amplitudes in cross sections are physical. So like they have an eigenvalue, a rephasing eigenvalue, which is their helicity. Yeah. So there's nothing weird that they're not invariant. We square them anyway. Yeah. Sorry, what's this? Yeah, yeah. Mm, mm. Right, right. I think it's I don't think it's equivalent, but it's definitely precisely the same spirit, right? So in conformal bootstrap or any kind of like even holographic context, there's like many arguments for the uniqueness of say corrections to gravity. That's a great example where we know that it's Einstein, Hilbert, Gauss, Binet, R cubed. Very reminiscent. The reason why I think they're both so rigid is just that both ways of doing things have a lot of symmetry. Lorentz was sufficient to fix it. If you add conformal, it's just even more. So I would, to me, it's like it's. I think it's secretly the Lorentz inside that's rigidly fixing it. I mean, we already had this, so like how much more rigid could it be? But it's so I would say the similarity is definitely in spirit. Conformal bootstrap assumes nothing but kinematics. This also assumes nothing but kinematics. Yeah. So maybe that's also a great thing for me to emphasize too. Like we usually think of 3-point as like a dynamics. We have this idea like there's kinematics, there's like Lorentz boost and like motion and velocity, and then there's totally different thing called dynamics, where I have coupling constants, and that's separate. Okay. Hopefully this conveys that is totally not true. Kinematics fixes interactions. Like kinematic, Lorentz invariance has fixed the interactions. Okay, it's not some separate idea. They're all the same and connected. Okay, okay. Good. Any other questions, comments? Cool. Obviously, we will go up now in spin. That's the natural thing to do. And it's essentially the same. In fact, you can already tell what's going to happen. Whatever. This is an important equation, but I wrote it. If we gonna double down on the spin, so 1 minus minus, 2 minus minus, 3 plus plus, okay? Or I can consider 1 minus minus, 2 minus minus, 3 minus minus, okay? Just, again, plug in all those expressions, what do you get? Well, you get, and again, this is something that should either, will surprise you if you haven't seen previous lectures, but should actually be obvious to you, which is exactly the square of the left-hand side, okay? So 1, 2 to the 6th over 1, 3 squared, 3, 2 squared. Okay. So why did that happen? Well, this thing was entirely fixed just by the helicities, okay? So if you want to double the helicities of an amplitude, at 3-point, you can just square it because all it does is square all the angle brackets and angle and square brackets. So if you square it, you'll just double the helicity weight, the little group weight. So it's a trivial way of just getting the amplitude. You square it, and this is the gravity amplitude. Okay, this is minimal Einstein's general relativity. Okay, this one here is also the square, except it's 1, 2 squared, 2, 3 squared, 3, 1 squared. And this is r cubed. This is the r cubed operator in gravity that I mentioned before, where r is Riemann. So the Riemann curvature cubed higher dimension correction to general relativity. Okay. Now, kind of noticeably missing from this is the thing in between, which was r squared. Okay, right? So there was some Gauss-Binet. I was calling it the Gauss-Binet correction, the two derivative correction in gravity. But as I also said before, it vanishes in 4D. It's a total derivative. So it shouldn't make an appearance, and indeed, it doesn't make an appearance. It's not here. Now you might say, wait a minute, let's go back to our old tricks. We saw before that we could take any product of Yang-Mills amplitudes and then get a gravity amplitude. So one product was just to square this, which gives us GR. We could take f cubed and square that, and that gave us r cubed. Why can't we take the product across them? Okay. Well, you can't because they have different helicities. Okay. So if you took this and you multiplied them, okay, they don't exist for the same helicities. Okay? In other words, if you track the helicity weight when you square these things, okay, so maybe more concretely, I'll say, if you took 1 minus, 2 minus, 3 plus, okay, and you multiplied it by a, 1 minus, 2 minus, 3 minus. You'd be like, all right, we're in good shape. We're going to get a 3 graviton amplitude in Gauss-Bonnet. We're like excited. But you can see just by helicity weight, okay, this is going to give you some mystery operator that has 1 minus minus, 2 minus minus, and then 3 spin 0. Okay? Because 3 plus and 3 minus means that one has plus 1 helicity, one has minus 1 helicity, so the net will be of a scalar. Okay? The resulting amplitude was not of a graviton. Okay? So you will get an answer, you'll get an expression, but it's not Gauss-Bonnet. It's a scalar coupled to gravity. Okay? In fact, it's axio-dilaton type coupling. Okay? So you can get them, they're fine, but it's not the theory of just purely gravitons. Okay? So that's actually another kind of nice feature here, which is whatever you take products of, you don't get just random things, you get things with names, actual theories. So you could take higher spins, you could take half spins. I haven't talked about fermions, but of course you could make these fermions. Okay, these would be quarks interacting with the gluon. You could have spin 3 halves if you want a graviton. Okay, you can do anything you want, and you can then multiply them and get the 3-point amplitudes in every other theory. Okay? All for massless particles. Okay, any questions about that? Good. So what have we learned? We've learned that 3-particle scattering is entirely rigidly fixed. We've kind of recapitulated some things we saw in 40 with a slight twist. But you know, if you're curious, you know, it's fun to just like plug in values of spins into these expressions and see how they accord with what you normally expect, right? A scalar coupled to a vector. Okay, any kind of random assortment, it could be somewhat illuminating. Okay. Yeah. Yeah. Spinor helicity is step 0 input of 4 dimensions. The fact that we can write P alpha alpha dot as a 2x2 matrix in SLT is like right at the gate. Yeah, yeah. It's a good question. You have to keep track of your assumptions. Had we started with 60 spinor helicity, we would immediately find other expressions. So like it's right at the gate. Yeah. Any other questions? Okay, cool. So this was all really straightforward. Let's do 4-particle scattering, okay? And it's going to tell us I'm going to try to convey like the conceptual reason first why 4 points fixed by 3 point, okay? And then we're going to jump to infinite point with recursion, okay? Which I will do. Yeah, we'll see how in depth I can go in those examples. Okay, so for 4 particles. Of course, what's the new element? So for 4 point, the new element is poles. Okay, we didn't have any poles. In fact, we went to a lot of work to like not have weird singularities. At 4 point, we have honest poles like 1 over s that we want, and by sitting on those poles, we can actually extract information about the amplitude. But we want to take again this kind of ansatz approach, but using spinor helicity. Okay, so. Let's do that. So let's consider an amplitude with 1 minus, 2 minus, 3 plus, 4 plus. Okay, I'm writing this down because we in some sense we know what the answer will be. This is of the form of the Park-Taylor type forms where we had 2 minuses and everyone else is plus. Okay, so we kind of know the answer ahead of time. We can confirm whether it's true or not. The idea of the bootstrap here is that we want to write a function that has the properties of little group rescaling that I mentioned, which means that this thing should rescale to t1 squared, t2 squared, t3 to the minus 2, t3 to the minus 2, sorry, t4 to the minus 2 times the amplitude. Okay, so in other words, this fixes some like net number of angle brackets of each type with these very specific homogeneity properties. Okay. Now, whenever in amplitudes we have a constraint like this, there's always a really convenient way to kind of trivialize constraints, which is just pull out a prefactor that has these kinds of invariances already inside it. Okay, so for this reason, we're going to take as our ansatz angle 1, 2 squared times 3, 4 squared times FSTU. Okay, the point here is that I'm pulling away just like a rational prefactor that has no poles. I don't have to like worry about adding poles accidentally. It's just a regular thing, which has exactly the little group weight to accommodate this factor. Okay, because I've separated this off, everything else doesn't have little group weight. Okay, and that would mean S, T, and U. In fact, just so we're on the same page, S here is P1 plus P2 squared. Okay, which was like angle 1, 2, square 1, 2. Okay, recall. And this has no little group weight. Okay, the always overarching intuition, if, in case maybe it's less familiar, is that things that have no little group weight are like scalar objects, like ST and U. ST and U doesn't have a chirality or a phase. It's just real ST and U. Or it's just ST and U. We think of there being a rephasing when there's kind of a spin in play. Okay, a pure scalar theory can be written purely in terms of ST and U, which is why it's made out of objects that clearly have no little group weight. Okay. Okay, any questions about the motivation for this ansatz? Yeah. No, yeah, good question. So, so I should say this statement here wasn't an assumption. It was derived from kinematics. So I went through it a little fast, but in my TASI notes, there's a whole paragraph that talks about it. But this was an implication of 3-particle kinematics specifically. At 4 particles, thank goodness, there's more interesting choices for scattering. Yeah. So we don't have to bifurcate into these 2 cases. In fact, it doesn't bifurcate. Yeah. There are certain cases, I should say, where a bifurcation can be thought of and understood, which has to do with so-called self-dual and anti-self-dual sectors, which is kind of the pure all plus and pure all minus sectors of theories. But in general, the full richness of the theory, there should be expected minuses and pluses. Yeah. Okay, so what's the idea now? So now we're going to use, so this was little group. Now let's use dimensional analysis. Okay, so dimensional analysis tells me that I know the mass dimension of F. Okay, how do I know it? Okay, so we're going to kind of argue based on what we've already assumed about 3-point. Okay, so if I just gave you 4-point and told you nothing at this point, like you don't even know anything about the theory, like you'd never be able to use dimensional analysis because you don't have the coupling constant. Okay, but implicitly, I'm going to assume that A, okay, we're going to assume that A, 1 minus, 2 minus, 3 plus is Yang-Mills type. Okay, we're going to assume that because we need to start from somewhere. So I'm going to assume, I had many choices to make of my 3-point. Let's assume the 3-point was Yang-Mills. Okay, we have to make that assumption. Once you've done that, you've learned that the coupling constant is dimensionless. Okay, if you just work it out, you'll realize the coupling constant, that FABC, is dimensionless in 4 dimensions, which means that we should expect a 4-dimensional amplitude that also has dimensionless coupling constants. Okay, so this is not assumption. This is just purely induction based on my input of 3-point. Okay, which has to be given to me. No one's going to tell me which 3-point it is. I fix one, and now I'm going to determine what 4-point has to be. So what this means is that since 3-point has the dimensions of a gauge theory, I know that 4-point has to have dimensions of the gauge theory. That's just the dimensional analysis. One way of seeing that is that if I took 2 3-point amplitudes and put them together, there's a dimensionless coupling in both. That's contributing to this. So this amplitude better have those dimensionless couplings. Okay, it's g squared, but still dimensionless, which fixes the dimension of f. So in fact, the dimensionality of f STU is actually -4. Let's see why that is. Okay, so there are 4 brackets here, right? There's 2 squared, so there's 4 brackets. 4 brackets means 4 powers of momenta, which is p to the 4th. Okay, so there's 4 powers of momenta here. I'm saying that f has to have 4 negative powers of momenta, so that the whole thing is dimensionless in terms of momenta. That is to say, the overall scaling of momentum is 0, so that the whole thing is completely dimensionless when I put a dimensionless coupling in front of it. Okay, so in other words, every time you have an amplitude, dimensions are produced by one of 2 things, the coupling constants or the kinematics. I've told you the coupling constants are dimensionless, thus everything's from kinematics, so F's dimension is fixed. Okay. So given this, I can now write down an ansatz for F. Okay, S, T, U. Okay, there's actually many ways of doing this, but let me parameterize it in the following way. It has to have -4 mass dimension. So let me write it in terms of all the possible objects I could have with poles that aren't manifestly illegal. Okay, st. I mean, you could use a bigger ansatz than this if you wanted, actually, but you just find that there are things that immediately get set to 0. Okay, so I want inverse powers of st and u. So these are of course obviously inverse 2 power of s and t. The reason why I'm not including 1 on s squared is the reason I said like last 2 lectures, which is double poles in this one variable is no good. Okay, because if I go to the s equals 0, I'll just get that double pole. It's not going away. It's just there. At least this only has a simple pole in s, but t is fine. It's finite when s goes to 0, and vice versa. Okay, so this doesn't suffer from those issues, which is why I've not included it. Okay. All right, good. Any questions? All right, so now we're ready to actually put some usage to this statement of factorization I mentioned before. We did factorization for that scalar case, which was really dumb and simple. Here we'll actually learn something, I would say, yeah, non-trivial about this theory. Okay, so 2 minus 3 plus 4 plus. We can multiply by s. Okay, this is I've been doing this a number of times, but let me remind you why we do it. I'm taking the amplitude and multiplying by s to pluck out the 1 on s pole. Okay, so this is multiplying the 1 on s pole, and then I take the limit as s goes to 0. Okay, so this is me just extracting the residue at 1 on of 1 on s. Okay, if you do that in this expression, in this ansatz, you get angle 1, 2 squared, 3, 4 squared, 1 on t times CST minus CUS. Okay, I should have said this, but these C's are just numbers, like constants. By dimensional analysis, this has no, like C doesn't have any STU dependence. It's just a number. It's like 7, minus 12, 14. They're just numbers, okay? Dimensionless numbers. Okay, good. So this is just what the ansatz spits out, okay? So this is like the idea. You write a big old function, go to the singularity, and then see what comes out of that function. Okay, so this is the value of the function on that pole, and then we set it equal to what we've assumed about lower point, which is that it's 2 3-particle amplitudes that have been glued together. Okay, so the idea is that we set this equal to a product, or really I should say a sum over all possible exchanges between the two. Okay, so let me write that a little more formally. So this would be the sum over 2 3-point amplitudes. Call it 1 minus, 2 minus, and I'll call this intermediate one P, and I'll give him helicity H. And then we have A, 3 plus, 4 plus, P minus H. Or we sum on helicity is plus minus 1. Okay, so these are 2 3-particle amplitudes. And I implicitly also have a color sum. Okay, so maybe not write it here, but when we wrote down the 3-particle amplitudes, which are now very much gone forever, we had structure constants, right? So there was actually a particle label, A1, A2, A3, the color structures, which means that you have to glue those color structures together, right? Like species A1 needs to exit 1 3-point amplitude and become species A1 on the other side. So we have a color sum connecting those coupling constants, okay? Also implicit in this piece, okay? Since I'm in the S channel, like 1 and 2 on one side and 3 and 4 on the other side, okay? So like that's why these are arranged this way. Now, if I look at the helicities, I have a piece that looks like minus, 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 and one that looks like minus, minus, plus. And again, depending on your theory, you could throw in all those amplitudes. But I want to take minimal Yang-Mills for the moment. So let me just keep the one that has minus, minus, plus. So like even though there's 2 helicities that could be exchanged, one would come from Yang-Mills, the other would come from F-cube theory, but let me not add that operator and just see what this is. Okay. Okay, so it's just a bunch of algebra, but the idea is like you take the 3-point I wrote, just plop it here, take the 3-point, just plop it down, and it's not super illuminating, but what you get is the following. Okay, let me just write the answer and then explain where it comes from. A1, A2, B, F, A3, A4, B. sum on B. Okay, so these are the 3-point color structure constants, right? Every amplitude had those indices. This B here is the one that's glued across. Okay, so this had a 3-point amplitude, it had a B label. He has to go across to the other side and connect. Okay, so this is just the couplings. Okay, but then if you just simplify and do a bunch of algebra, you find nicely that this equals 1, 2 squared, 3, 4 squared, 1 on T. It just takes a couple Schouten identities and momentum conservation, but you get to here. Okay, if you have questions about this, just go to my my TASI lectures where it's like spelled out step by step. But it's not super illuminating. Okay, now here's the point. We compare these two things now. Okay, we have one expression, which was the Ansatz's limit on the pole, and the other expression is what we want or need to demand in order for factorization to be consistent. Okay, so this is where lower point gets fed in. And this is where our Ansatz structure gets fed in. And we use this to solve for the Ansatz structure. Okay, so in other words, this is a relationship that lets us solve for the C's. Okay. So what do we get? We get a bunch of equations for C's, for the C, CST, and so on. So we have, for instance, CST minus CUS equals sum of F. Okay, let me not, again, I don't want to spend all day like writing indices, but like this same F structure right here, okay? But we have other equations, right? Because I just took the S channel, but I could take T and U, I can take all the other channels. And if I do that, okay, what do I find? I get more equations just by kind of crossing and doing the same exercise in other channels, okay? In fact, let me actually write this out because it's probably worth seeing. This is A1, A2, B, A3, A4, B. This is A2, A3, B, A1, A4, B. Okay, and last but not least, we have CUS minus CTU, which is equal to the last permutation, which is A3, A1B, F, A2, A4B. Okay, just a lot of algebra here. Okay, but why am I writing this out? Well, I'm writing this out because these equations actually tell us something deep, shockingly, which is let's add these equations. Okay, let's just add these equations up. All three. If you add all the equations up, like literally left-hand side add up, you'll of course cancel every term. This cancels that, cancels that. So 0, okay, 0 on the left-hand side, equals a certain 3-term identity involving structure constants. Okay, which involves cyclically permuting 3 of the indices of the structure constant. Okay, yeah, I'm not going to rewrite it here, but this of course has a name. This is called the Jacobi identity. Okay, Jacobi identity. Okay, so where does Jacobi identity normally appear? Well, it usually appears because we say the majesty of the gauge symmetry principle, and then we write down a matrix, like a Hermitian matrix, an SUN gauge theory, and then we take commutators and we say, wow, Jacobi is it's an identity. You just take commutator algebra of matrices multiplying each other, Jacobi pops out. That wasn't obvious here because we never started with QFT. Okay, in fact, you might have mistakenly thought that that was somehow negotiable. Like, you know, maybe we could have deformed that in some way. No, that's not true. Jacobi identity follows from factorization. So in other words, if someone said, I have a gauge theory and I have a structure constant, but it doesn't need Jacobi, like I can modify it and break it, well, you can now go through this analysis and be like, well, where did your theory violate factorization? Okay. Yeah. Sorry, what was that? Yes, that's precisely in the Jacobi identity. So in the Jacobi identity, you have 2 F structure constants with the sum, and then the sum's crucial. Yeah. One way of seeing that is you can think of each of these matrices as adjoint representation matrices, in which case this is actually matrix multiplication. But yeah, the sum is crucial for the Jacobi identity. Yeah. Is there a minus sign between these two? Oh. CST minus CUS. The minus sign. Oh, yeah, yeah. Because the pole actually has -1 residue. Very good. It's so funny. I think this is a typo in my Tassie notes. Let me not commit to that minus sign. Yeah, I wanted to fix that like years ago. But yeah. What's that? In the bracket. Oh, the relative sign between these two, you're saying it should be swapped? Um, no, no. So this is this first term, CST over T, comes from extracting the S pole. The other term with S has a U in it, but U goes to minus T. Yeah, yeah. So it's actually that's a thanks for bringing that. That's a good like just like in technical operations when you're taking these limits. Yeah, S goes to 0, but also keep in mind that U is also, since S is going to 0, going to minus T. Yeah. There's also, I should say, be warned, there's a minus sign also that I was worried about because of conventions about like whether the pole is +1 or -1. But modulo that, which is some overall thing, this is still true. Cool. So what have we learned? We've learned that the two most important facts about gauge theory, that there's a structure constant, there's a gauge group. We've learned about the gauge group. There's a gauge group, there's some set of objects F which define it, satisfies Jacobi, and that's required for consistency at 4-particle scattering. Good. Let's do gravity now. Okay, yes. Yeah, for sure. Yeah, definitely. So in principle, you should sum over any state that you have already decided existed at lower point. And it's your choice. And no one can tell you which one it is. It's like, yes. Yeah, all of this is tree level for sure. Yeah. So all this is tree level because even the factorization condition itself hinges on tree level. So for sure, it's tree level, just at full stop. Right. So let's say you were in an effective field theory. We had composite states that still had some effective description with the tree level notion. Okay, like you're in the Chiral-Lagrangian or Baryon-Chiral perturbation theory with states exchanged. Then indeed, you could have a whole tower and you'd have to include them. In order to include them, you have to know their 3-particle amplitudes to see how they factorize. So yeah, for sure. Yeah. So even in a tree, and in fact, this would happen, and I may even get to this, like in a string amplitude. Okay, so in a string amplitude, I could talk about, some states in the bosonic string or the superstring which are scattering, but the external states could be scalars or vectors or something simple. But we know, even in the tree level approximation, there's this big old tower. You have to add all of them up, and you have to know all the states in between. Now, fortunately, we know the structure of all 3-particle amplitudes. We've already decided that, even for the massive case, which I haven't talked about, but that's also known. But yes, you decide what the spectrum is, what the 3-particle amplitudes are. Well, we know their structure, but you got to decide what coefficients to put in front of each, and then everything else here is dictated. Yeah. Yeah. What are so like what is the true underlying physical reason for factorization? Yeah, I would say the technical way of saying it would be cluster decomposition, as in like Weinberg, whatever, volume 1, chapter something, low chapter, a low chapter of Weinberg, where he very crisply and technically goes through all the details of like why is it that why can we talk about particles when we convolve them into like into wave packets and so on. So I think fundamentally it's that, because when two states are produced and you produce a state that's on shell, it's basically just producing a state that's going a great distance, right? The idea is it's like any resonance. In any resonance, when something hits a singularity and you hit on resonance, you're actually dead on resonance for exciting a state. You're like populating some resonance state, and it's then decaying. But that big infinity is really just, it's like propagation in time and space. So like if you, for instance, if you rewrote this 1 on S, and I may have mentioned this in Schwinger time parameterization, you'll just see like it's the long time piece, which is like going to make that thing blow up when S is 0. Yeah. So that's the physics of it. But if you want like a crisp technical answer, then it would be found in Weinberg. Okay, very good. So let's do gravity. Gravity turns out to be way faster, which is nice. It's one of the illustrations of the more spin, the easier. Okay, right. Normally in physics, like in Feynman diagrams or QFT, like the more you go up in spin, everyone starts getting more nauseous and kind of starts sweating because spin 1, oh great, easy. Spin 2, everyone's like, oh. Spin 3, people start panicking. It's the opposite in amplitudes. The higher the spin, the more constrained it is. Why is that? Essentially because the little group forces very high powers in these T's, and those very high powers always require spinners to rephase under them, which increases the dimension, which generally constrains the ansatz. Okay, so in fact, let me show you what I mean by that. Let's take A for what would putatively be a graviton. 2 minus minus 3 plus plus 4 plus plus. Okay, I've just doubled all the spins. We can do the same trick here. I just put more spinners. Okay. Okay, it's like kind of just wisely writing down the right object. 3, 4 to the 4th times f of STU. Okay. Now, again, I'm going to be using prior knowledge, or I should say a prior assumption about 3-point, because of course at 3-point, I have to decide what is my 3-point couplings for this spin 2 state. And I'm going to assume it's GR. Okay, I could have assumed it's R cubed. I mean, you could actually try to build a theory like that, like a theory whose first interaction is R cubed. That actually is a theory. You could build a theory of, okay, this isn't for everyone, but there's a theory of linearized tensor, basically the graviton field strength, to any power. Okay, it's a little bit like the Euler-Heisenberg-Lagrangian, if you know what that is, but for Riemann curvature. So there exist theories like that, but let me not assume that. Let me just assume this is like Einstein's good old general relativity. This thing, again, I'm not going to go through that, write it down again. We know it had mass dimension that was 1 on m Planck. Okay, I'll leave that to you to see, but if you just count all the spinners and look at the mass dimension, you realize you need a 1 over a mass scale to make that thing have right dimension, which is 1 on the Planck scale, okay, which is the coupling constant in gravity. What that means is it then fixes the dimensionality of this capital F. Okay, so let me again tell you what that dimensionality is and then argue why it's true. This is, in this case, minus 6. Okay. The reason why is that these have 8 powers of mass dimension. This minus 6 cancels that to give me 2 powers of mass dimension, which is exactly what I need to cancel the 1 on m Planck squared. Okay, or the g Newton in front equivalently. Okay, but so again, it's a little fast, but trust me, this thing is mass dimension minus 6 if you've made the assumption that 3-point is general relativity. Okay, so it's not a guess, it's just a fact. Okay, so now F, yes? Yeah, so it's fixed by the fact that in 4 dimensions, I think this was one of my first axioms, the dimensionality of an endpoint amplitude is 4 minus n. Sorry, my brain is gone. Is 4 minus n. So a 3-particle amplitude has mass dimension 1. Okay, so in fact, let's just write this out. This thing is angle 1 to the 6th over 1, 3, 3, 2 squared. Okay, so this has mass dimension 2. Okay, the kinematics here has mass dimension 2 because there's 6 angles here, there's 4 angles here, leaving you with 2 angle brackets, and 2 angle brackets is 2 momenta, which is 2 powers. So this thing goes as p squared. In order to get for A3 dimension 1, I need to divide this by m Planck. So this is my dimensional constant, so mass dimension 1 object in denominator. When I put 2 of them together, I get a 1 on m Planck squared. And that is what's going to make up the rest of the dimension. Okay, so yeah, kind of sitting, yeah, I should have said, like sitting, here I'm extracting out the 1 on m Planck squared, so this whole thing has to have a net mass dimension 2. Okay. Any questions about that? So yeah, I guess they just flesh it out now. So there's no assumption, I'm just taking it as input. 3-point has dictated this dimensional analysis. Now, what could F be? Well, it has to be a mass dimension minus 6 expression that doesn't have double poles or triple poles. And the only crossing symmetric, that is a fully symmetric object you can write is 1 on STU, which is the answer. Okay, so that then fixes gravity up to an overall normalization. Okay, so in some sense, this is even easier because I don't have to even check factorization because there's no other function you could write. Okay, so in other words, the 4-point graviton amplitude is just angle 1, 2 to the 4th, 3, 4 to the 4th over STU. In fact, I think I may have written this down as like one of the simple formulas that you see just in amplitudes. But here you can kind of see why it's true. Okay, there's no object you could have written here that didn't have this helicity weight, the appropriate helicity weight for gravitons, and didn't have double or triple poles. Okay? And of course, you could compute this a hard way with those 100 kilobytes of terms, and then it equals this. Okay, it's almost frustrating how much it simplifies. Okay, yes. Right? What's that? 1 over S. Oh, 1 over ST. A number over ST. 1 over ST squared. Good. This would have a double pole in T. Yeah. So if you like, you could always, I mean, it's worth exercise, like put all that in, and then do this bootstrap by demanding no triple poles, no double poles, and then it will smoothly iron out everything except this. Yeah, another question? Yeah. 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 To fix the dimension you did. Yeah. Yeah. Oh, that's a interesting proposal. I think yes. I mean, in the off chance that you can fix things this easily, you could reverse. Just be like, well, I just read a 4-point. What is it? And then discover 3-point. Indeed. Yeah. I think that seems logically consistent. Yeah. But it's telling you how rigid gravity is. Like gravity is like really, really rigid. Okay. Good. So let me keep pushing ahead. Okay. We've gone to 3. We went from 3-point, showed it was totally unique in a really nice way. We now showed how 4-point is like blessed with that uniqueness without real issue. Let me comment on something. Oh, I kind of said this already, but let me just emphasize it. Not everything is unique. Okay, what's a thing that's not unique? Phi 4. Okay, we went through the scalar case, and we saw that once you fix the factorization piece, there was still a freedom at 4-point, which was just like, do I add a contact Phi 4 coupling? Now that might bother you. Be like, wait a minute, I can't construct lambda Phi 4 from factorization. Well, you were never expected to. Lambda in Phi 4 theory is not fixed by anything lower point. Like there's nothing here is magical. This is all, I assume that lower point is there, so it constrained higher point. There are certain things at higher point that are not constrained, like the Phi 4 coupling. In fact, if someone said, I use 3-pointology to determine lambda Phi 4's lambda coupling, that just would make no sense. Like, how would you do that? It's an independent factor that has nothing to do with lower point. Okay? So in theories where things are fixed, it'll be fixed. And theories where they're not, it'll be free. And every time you encounter a freedom, that's called a coupling constant. Okay? So in this way, you can build effective field theories. Just like we built F cubed in Yang-Mills and the leading term, that was just like, we don't know what this new object is, let's strap a coupling constant on it, it's just a new operator. Okay? That's just the philosophy. Now, in some cases, as you go higher and higher at endpoint, you never encounter new objects because at least if you fix the dimensional coupling, it's a uniquely constrained theory that has absolutely no rigidity, and that is the case, as it turns out, and as you might imagine, for Yang-Mills theory and gravity. So the structure we saw of Yang-Mills and gravity is still fixed at 4-point from 3-point, continues to 5-point, 6-point, and on. You could show that by just doing this painstakingly. Like you could just suffer through, like, go through every channel, check everything, and match. That's hard. Turns out there's a much better way to do this, which is called on-shell recursion. Okay, and This ties in with what I said in the very beginning, where I had advertised. I said, there is a 5-point Feynman diagram expression, it's horrible. Here's a beautiful expression. Wouldn't it be amazing if there was some formalism that spit out the nice expression, okay? This is the formalism, okay? And I can tell you mechanically why it's simpler. It's simpler because the inputs, like the very thing you input is not polarizations, of course, but these nice 3-point amplitudes and Park-Taylor formulas, okay? They're things that are already compactly elegant, and we're going to recursively build higher point from lower point. So it's always going to be these like angle bracket expressions that get squished together nicely. Okay, so that's just like at a technical level why they look better. There's never some giant polarization dot product with momenta anywhere. Okay, I should mention maybe just historically, there of course exist recursion relations for Feynman diagrams. I mean, the first time you encounter Feynman diagrams, you could already see these are recursive objects, right? If you compute the 3-particle Feynman diagram off shell, you can always feed it into 4-point. You can recycle, right? To get 4-point, you take the 3-point, glue it. You just keep gluing. In fact, in a problem set, that's what you do. You don't like start from the beginning again each time. You use what you learned at lower point at higher point. The name for that technically is called Behrens-Gieler recursion, which is essentially just recycling Feynman diagrams from low point to high point. I may return to that because it's deeply connected to equations of motion and actually some interesting things and facts about general relativity. But I'll just mention to be responsible. The recursion has always existed in physics, as you can imagine. But this on-shell recursion is of a slightly different type. And here's how it works. Okay, and I'm gonna write it in the most abstract sense first. Okay, so imagine you have an amplitude that depends on some variables. They could be lambdas and lambda tildes. In fact, that's maybe the key example I'll look at. But more generally, let's even consider just momenta, okay? Just because I'm trying to tell you a basic idea. Okay? So imagine I had, say, like an amplitude that depends on, if it's scalars, there's not even polarizations. If you wanted polarizations, I can put them in too, but just imagine them some set of p's. Okay, and imagine pi or on shell, okay? So like they have like numerical values, let's say, or whatever, values that are on shell. What I want to do is deform them in a way that probes different kinematics of that amplitude. What you could, of course, do is just shift pi by delta pi. You take all the momenta and just like throw them around, okay? Now, if you do that, you'll generally leave the on-shell surface, right? Because you can't just willy-nilly just change the momenta. You have to conserve energy, momentum, keep on shell, and so on. So what we want is a way of deforming pi that is automatically on shell, okay? So in other words, we want to shift pi in some way that very slickly knows it's like keeps on shell, so you're never doing an illegal move, and always are talking about something physical. So what we do is we take P and we shift it, we send it, this is called a complex deformation, P of Z, where in the kind of the simplest examples, it would just be a shift by ZQI. Okay, so Pi here is just that vector, look at the 4 momentum or whatever, d momentum in d dimensions. Qi is another reference vector, some other choice. And z is going to be a complex number. Okay? It's going to be our 1 parameter, label for a family of amplitudes. Okay? So like when I move z around in the complex plane, I'll be probing different kind of kinematics. Okay? Now, of course, this thing will not in general be on shell. I just did what I said we shouldn't do, which is just shift this randomly. But we can make it on shell. Okay, so we can make it on shell. So in other words, this will deform the amplitude to a of z. Okay. In general, if we have no constraints, this is not even an amplitude anymore. It's just some garbage. But we need to place constraints on these q's and p's, on the q's, in order to keep this on shell. Okay. So for instance, we want to maintain momentum conservation. We want to maintain momentum conservation, and what is that? That's a statement that if I sum p I of z, okay, my deformed momenta, over all momenta, 1 to n, then it should be 0. Okay? Which is just a statement that the sum of qi is 0. Okay, so just one constraint on the q's. They better sum to 0. It just says deform all the momenta, but in a way such that the total momentum is still 0. Okay? There's a second condition, which is the on-shell condition, which says that pi squared of z, if I square this, it must be 0. Okay, and that means just square this object and demand that it's still on shell, which tells us that qi squared equals qi pi equals 0. Okay, so these are constraints we have to impose. Okay, so like they're not overbearing constraints. They're like relatively minor constraints. I can always define the last q based on this equation, and I can be clever with the q's to satisfy these equations. Maybe just to emphasize why it's clear that such a basis exists, polarizations satisfy identities just like this, right? Polarization squared is 0 for helicity polarization, and it's orthogonal to P. So like we can construct actual explicit momenta that do these. Okay, so if you like, this almost looks like a set of polarizations which sum to 0 and are also have the properties of polarizations. Okay. But if we impose these two box constraints, then for any z, this thing is still, by any measure, in amplitude. It's just been deformed somewhere else in kinematic space. Okay. Now here's the key move. Okay, and maybe I'll say this before we like it's a good place to take a break after this. We now do Cauchy's theorem. Okay, so Cauchy's theorem tells you that if you have some function, some let's say meromorphic function in Z, so it's something which only has simple poles in Z, then we can apply Cauchy's theorem. The reason why this thing has simple poles is that A, as a tree amplitude, I should emphasize this is tree, is a rational function of momenta, which means it's a rational function of Z. So this is just a rational function of Z. It's a polynomial of Z divided by another polynomial of Z. And we know that the properties of a function at one point are related to the properties at another point by Cauchy's theorem. Okay? So the essence, if you ever heard the words BCFW recursion or on-shell recursion, they all use exactly the same trick. In fact, it's the same trick as dispersion relations, if you've heard that, or positivity. These are all exactly the same trick over and over, which is the following. A when z equals to 0 was the original amplitude. Okay, that's my goal. I want to get that thing. So that's the thing I'm trying to compute. So let me compute it in a naively oblique way, kind of a strange way, but one that will pay dividends, which is take the pole at z equals to 0 of a of z over z. Okay, this is just like an identity. Okay, just pick out the pole at 1 on z, there's a pole here, and just extracts a at z equals to 0. Okay, this is the residue theorem. Okay, so that's fine. That's just a tautology. But a of z here, okay, if we just think about this function a of z over z, if we just plot it, plot it in the complex plane, right? A over z, az over z has a pole at the origin, okay, and I'm basically drawing a contour around this. Okay? I'm picking up that contour. It seems like I haven't added any value. But we know that the a of z has other poles. Okay, why does a of z have other poles? It has other poles because amplitudes have poles, right? In other words, as I move this z around, every now and then I'm just going to hit a resonance. Okay, like I can just move z and just see when I hit other poles. Okay, because the function a has poles corresponding to actual particle exchanges. So in other words, this thing is speckled with zeros all over. There's all these zeros everywhere. Okay. Sorry, poles, not zeros, poles. There's all these poles everywhere. One of them I inserted by hand, but the others are coming from A of Z. Those poles have physical information. Okay, those poles are factorization channels. Okay, like this is one factorization channel. This other pole is a different factorization channel. Okay, so there's like each of these poles is a different factorization channel. Okay. So they all have meaning. But the key point is that if I now apply Cauchy's theorem, I can write this as the sum over all of the other poles that aren't at 0, which tells me that this is the residue of a of z over z for z equals zi. Okay, so I'm labeling each of these poles by zi. Let me call this zi. And capital I runs through all those poles. Okay, capital I is running over those poles, but it's secretly running over every singularity that I can hit with z. This is all those residues plus a term at infinity. Okay, right? Because when we apply Cauchy's theorem, we take this thing and we blow it up. We pick up all the contours, but there's always a boundary term at infinity. Okay, the residual contour at infinity, which we call b infinity. Okay, so the amplitude that we want to compute can be computed in a new way with this formula. It says take an amplitude, like take an amplitude that's your target. I want the 5-point amplitude. I don't have it yet, but I want it. Well, thankfully, I can write the 5-point amplitude in terms of residues at its poles, which happen to be made of lower point amplitudes. The point is that these residues are not the 5-point amplitude. They're products of 3-point, 4-point. Okay, so this is all lower point information. This is why this is higher point to lower point. Okay, by relating something to its singularities, you've related it to lower point information. The plus b infinity is a term that's just very annoying, and yeah, there's no other way to say it, but turns out to vanish in theories. Okay. You can argue for why that is. In many theories, it doesn't vanish, but there's always a correlation. Typically, in theories where this b infinity never goes away, it physically is like in an effective field theory where there's ultraviolet sensitivity, and you could write other operators. Okay, why do I say that? Okay, let me clarify what I mean by that. Let's say that b is never present. Okay, so I work at 5-point and I rate in terms of 3 and 4 plus 0. That's great. Now I go to 6-point and I write in terms of 5, 4, 3 plus 0. Obviously, this fixes the whole S matrix. Okay, and for gravity and gauge theory, that will happen. This boundary term will be 0, and you will generate all of general relativity, 50-point from 3-point. Okay, all of gauge theory from 3-point. Okay. In other words, there is no information in Yang-Mills in gravity other than what's in the 3-point amplitudes we saw. That's the whole thing. There's nothing else. There's no extra ingredient. Now, there are other theories where that will not happen. Okay, so for instance, if you had just a random theory of scalars with lots of derivatives in effective field theory, we will typically find this b infinity is not 0, which means that we'll have some extra piece that we can keep feeding in, which is unknown, and those are Wilson coefficients. Those are secretly telling you about freedoms, which tells you that higher point isn't fixed by lower point. There are other operators you can write down that will change the dynamics, otherwise known as higher dimension operators. Okay, why don't I pause there? It's probably a good place to pause. And then we'll come, when are we coming back? 15 minutes, yeah, cool. I can take questions too, but yeah, we can wait 15. All right. Right. Cool. All right, let's start. So welcome back. Let's pick up right where we left off, because I actually really did want to reach the other topic. In my next is it an hour? I have 1 hour. Right? 1 hour. Yeah, 1 hour. Great. So yeah. So where did we finish off here? So we finished off by defining a general principle whereby we can deduce a higher point amplitude, which is this A, in the following way. What we do is we deform all of its momenta by some complex parameter z, and then we do complex analysis on that z. We evaluate the amplitude at z equals 0 by plucking out the pole at 0, and then we blow up the contour to pick up all the other poles that this higher point amplitude has. As a consequence, we get a bunch of terms that are residues at those poles, and as I've said many times, poles in the amplitude come from products of lower point amplitudes. Okay, so in other words, this residue thing is stuff we already know inductively. Okay, so if we have some higher point stuff equals sums of lower point stuff plus some boundary term b infinity, okay, which I'll get to in a second. Now let me maybe I'll just take this. I'll be a little fast here, but you can evaluate these residues, take care of all the various Jacobians and factors, and find a very nice compact formula for what this expression says. And what it says is the following, which is like, in other words, I'm unpacking what this residue term is. You have a product of amplitudes, A left and A right, okay, which are evaluated at Zi, sum on I. Okay, so let me write it out first, and then I'll explain what it means. Divided by pi squared, okay, plus b infinity. Okay, so this is just the residue term I've rewritten, where left and right are defined in the following way. So the idea is that you have some endpoint amplitude here. Okay, this could be, for instance, a 6-point amplitude, and I'm writing it as a sum over terms which have factorized into two pieces. Okay, so this could, for instance, be 3 legs on one side, the other 3 legs on the other side, and then across. Okay, so in this language, this thing is A, this is A left, and this is A right. Okay. So there's many terms like this, okay, and each one is labeled by a capital I. Okay, so capital I is labeling my factorization channels, each one that I can hit, and on that factorization channel, z takes on some value, which is zi. You can compute it. Okay, how do you compute it? You can compute it because you know that it. Let me say this implicitly. Okay, again, I won't go to this in too much detail, but there is some on-shell condition where if I take pi squared of z and set it to 0, that is basically saying the exchanged momentum at that value of z is on shell. Okay, this is me moving z around until I make that intermediate leg on shell. So this is 0. And maybe if it wasn't clear, this here is actually z equals 0. Okay, so this pi squared is not infinity. Again, if you want to see the maybe a half page of derivation, it's again in my TASI notes. But the point here is that there's now a very super explicit formula which says higher point equals sum of product of lower point. Okay. Now, it looks very similar to Feynman diagrams, certainly. You might confuse yourself that it truly is. But here's why, at a technical level, it's always simpler than Feynman diagrams. Okay. If you take a Feynman diagram and you compute it with a Lagrangian, you get some expression. As I said before, if you change field basis, change gauge, do lots of redundant things that shouldn't matter, the off-shell Feynman diagram changes. It just looks different. Okay? These are all on-shell amplitudes. Okay, so A, AL, AR. These are as nice as any of the angle bracket, square bracket objects we showed. They're all on shell. All their external legs on shell. So in other words, when I talk about A left here, every leg, including the intermediate leg, is on shell. These are all on shell. Consequently, everything looks like Park-Taylor, beautiful expressions. They're just nice expressions. So that's the first kind of technical difference. The second technical difference is that this sum on I doesn't have to run over every single pole that you would have thought was there. Why do I say that? Well, normally we think of an amplitude and we think it could have like S channel poles and T, and you would imagine every single pole is there in this function. But when we deform by z, we aren't guaranteed that z can hit every pole. Okay, right? I just kind of chose some set of cues. You can easily imagine that z could hit some poles, like the pole in the S channel, but not the pole in the T channel. There's no reason it has to see every pole. That may seem strange, but it's actually an advantage. Okay, why is it an advantage? In Feynman diagrams, we implicitly sum over every single factorization channel. That's why you say write every topology, every single one. Here, we generally sum over less than all the topologies because this I doesn't run typically over all of them. Okay? In fact, in the nicest versions of this, it sums over many fewer diagrams. And it's, again, for this reason that try as you might, Z cannot make all the momenta squared vanish. It just can't get some to vanish. So despite that making it sound like ineffective, it's actually good. The fewer poles you hit, the better, because there's fewer terms you need on the right-hand side. Okay. Good. So let me comment on first the spinor helicity version of this, just super quickly, and then B infinity, which I did talk about a bit, but then so again, this is maybe if I had more time, I would like work through like a super concrete example. If you want to see a super concrete example, you should look in Elvang and Huang's Scattering Amplitudes book. They have exercises, but the mechanics of it is like, this is a nice angle bracket expression, nice square bracket expression, multiplies. I mean, it's just more algebra. But the point is, this will all look nice, so this looks nice, and then you apply recursion. Yes? Very good. So let me show you, actually. That's a great question. In fact, it's simplest if I first define BCFW, and you'll see which poles are missing. Yeah, so let me do that. That's a very good question. Okay, so Yeah, let me put a button in that and then we'll return to it in about 1 minute. Okay, so BCFW is the most famous and well-known recursion relation, and it corresponds to the following choice. Q1 equals minus Q2, okay? So it actually involves only shifting two legs. Okay, this is what's kind of cool about BCFW. No one said everyone has to be shifted. In fact, if you think about it, your goal should be to be as to do as little damage as possible and introduce Z as little as possible. Okay, so ideally you'd shift one momentum, but you know you can't shift one momentum while maintaining momentum conservation. So you have to shift at least two. So you shift the two and you have them equal and opposite, and you define this to be the following: lambda 1, lambda 2 tilde, okay, in terms of spinners. Okay, it's some kind of like crossed version. It has a 1 spinner and a 2 anti-spinner. We can write this in terms of a shift of the angle brackets. Okay, so here's what's interesting. So this is me saying in terms of momenta, but we can write the shift as in the following way: lambda 1 tilde goes to lambda 1 tilde plus z lambda 2 tilde. Lambda 2 goes to lambda 2 goes to lambda 2 minus z lambda 1. Okay, so you know in the previous slide, this up here, I was talking about shifting p's. But if we're using spinner helicity, p's are not our variables. Our variables are angle brackets and square brackets. Okay, so we should be shifting our angle brackets and square brackets. This is the BCFW shift. It says, ignore everyone except two spinners, lambda 1 tilde and lambda 2. But for these, shift them in the following way. Okay, now here's one key point. The on-shell condition is automatically satisfied. Why? If I give you like some lambdas and I just change them to other lambdas, by construction, spinner helicity keeps everything on shell. That's its whole purpose in life. P squared is 0, always. It doesn't matter if I take, right, when I say P equals lambda, lambda tilde, P is on shell. If I make this lambda prime, just change it, it's still on shell. It doesn't matter what their identities are, P is on shell. Which means that when I send lambda 1 tilde to something else, it's so the on-shell conditions are all great, automatic. The one thing you have to check is momentum conservation, which is precisely why this thing here, this thing implies that Q1, well, I already wrote it up here. Q1 is lambda 1, lambda 2 tilde, and they're equal and opposite. So these opposite signs here are precisely what maintains momentum conservation. Okay? Yeah, if you want to see for yourself, I recommend just turn these back into momenta and just see. You should see that this thing stays on shell and momentum conserving. Okay, any questions about that? Okay, so the claim now is you can take any of these nice angle or bracket expressions and just do this shift to them. Like you just, everywhere there was a 1 bar, send it to plus z 2 bar, and so on. In doing so, you will have gotten a of z. You could, of course, evaluate z at 0, and that's the original amplitude. But you can instead extract all these different poles by floating z around until you hit singularities. Okay. Now, there was a question of which poles do you know you hit beforehand, a priori? Well, let's think about that. So let's say you have some endpoint amplitude, and you're asking about a factorization channel. Okay. So by definition, what you want is to be kind of scanning z and to hit this channel, this intermediate channel. So let's just like take examples, okay? Let's imagine legs 1 and 2 are here. Okay, that's reasonable. Let's imagine, let's consider this diagram. 1 and 2 are on this side. Well, if 1 and 2 are on this side, okay, then they show up together, which means the momentum flow through here is P1 plus P2 plus other stuff. Okay? Which means that when I shift P1 and P2 by Z, this shift exactly. So in other words, this is the same as P1 of Z plus P2 of Z plus all the other stuff. In other words, the Z dependence cancels. Okay. By definition, I shifted P. I shifted P1 and P2 oppositely. So when they come together, that shift cancels, and there's no Z dependence in this pole. Okay, there's no Z dependence in this propagator. What that means is there's no choice of Z that will make this thing go on shell. Okay. In other words, like take Z to be whatever you want. Z doesn't even functionally enter into this pole, this 1 on P squared pole. Just cancel. Okay. The kind of contrapositive of that statement is that the diagrams that do cancel have to have 1 and 2 on opposite sides. Okay, so in contrast, if you had something like this, where this was 1 on this side and 2 on this side, then you can think of there being like Z flow, okay? Like there's some ZQ shift that like passes from 1 and through here. There's some ZQ that flows through. This propagator will depend on Z, so you can choose a Z that hits the pole. Okay. So to answer your question, the factorization channels that need to be included are the ones which are on opposite sides of a pole. All that means is, I mean, really physically, is like you had some apparatus with some set of momenta, you deformed the momenta, but that deformation has to leave the diagram somewhere by momentum conservation. And you just want to make sure that flow goes through the pole so that you can hit the singularity. Now, that means a vast reduction in number of poles, okay? Just because anything where 1 and 2 is on one side or the other side is gone. So there's just fewer. It turns out for BCFW applied to Yang-Mills, which has convolved into it some other nicety having to do with something called color ordering, which I won't elaborate on, has a Catalan number of diagrams, which is way less than the number of Feynman diagram topologies, which is like 2n minus 5 double factorial. It's like way, way less. Okay. All that counting, by the way, you can also find in my TASI lectures if you're interested. But like just at the level of literal diagrams, it's fewer, and each diagram is simpler. Okay. So in fact, maybe I didn't write this in my introductory slides, but if you just do accounting, like compare Feynman diagram number of terms to like recursion, recursion just has fewer terms and they have more compact expressions. Okay, so that's a benefit in some cases. I mean, at some point there's always diminishing returns, but they're relatively compact. Okay, good. Yeah, I could like return to B infinity. I have a whole spiel on that, but maybe I should move on. But the kind of upshot in terms of theories is that B infinity is 0 for lots of great theories that we like Yang-Mills and gravity. Okay. Typically, if we have a theory which isn't pure gravity, but has just higher derivative corrections or just extra stuff with free parameters, we just know logically that this can't be enough to construct everything. Why? Because higher point is only uniquely fixed from lower point if there are not higher point Wilson coefficients I can add to spoil the fun. Okay? And indeed, in minimal GR, its definition is that there is no other corrections. Okay. So indeed, if you look at gluon graviton amplitudes like explicitly, you'll find that this B infinity vanishes and for an appropriate choice of helices and shifts, which I won't get into. But the kind of broader terminology amplitudes for the case when B is infinity, B infinity is 0, is called on-shell constructible. So people often use this term. They'll say a theory is on-shell constructible. And what they always mean is the kind of dream here, which is you start with 3-point and just bootstrapped up to like a unique expression, and then higher point was all fixed from 3-point. Okay. And this is now, I mean, you can see structurally, this is general relativity from what? Okay. We have the full endpoint graviton S matrix through this definition. Okay. This is how people compute in the business with this. Secretly, this is all the nonlinearities in Einstein's equations. But we didn't have elevators or like thought experiments. We had nothing. All we had was Lorentz invariance, massless spin 2, self-interacting at 3-point. Okay, everything else followed from it, and dimensional analysis. Okay? So that's very powerful. Okay, and that's at least a different way of understanding things you know, which kind of at least, I mean, in some ways takes the wind out of how special they are, but also makes them more magical. General relativity is beautiful, elegant, and has deep insight. But it's even more amazing because it can't be deformed. Like, it's unique and beautiful, which makes it even more incredible. Okay, good. Any questions about any of that? About recursion or the bootstrap? Because I'm about to shift gears. Yeah. Very good. So that's a fair question. This is 0, and this is all constructible from a flat background, for sure. So this is a derivation of general relativity as the effective field theory about a flat background. You could, of course, build the Lagrangian from that, realize it can go to strong field and get curved space geometry. But yes, like the input is definitely flat space and then all perturbations about it. So it's a perturbative analysis in that sense. But it can go to any height point you want, okay? Any endpoint you want. This BCFW recursion like technically is useful, but it also is great for proving things. Okay, so often people in S matrix program will say things like, "We prove this for all the S matrices." They'll say these, and you'll be like, "Wait, how did you do that?" 9 times out of 10, we have recursive formula, so you can write down induction formulas where you have, I think this amplitude has a property at arbitrary number of particles. So you assume the property, apply recursion, and then prove it. So this is kind of a very nice proper tool, one that is harder sometimes with other methods. Yeah. Okay, any other questions? Yes. Why should you care about what? That's your personal choice. Yeah. Yeah, yeah. Oh, experimentally. Oh yeah. Yeah. Oh, very good. Yeah, yeah. Why would you ever want to compute it? So as it turns out, the state-of-the-art calculation in powers in G Newton that is if fed into the LIGO pipeline and now being compared with numerical relativity and so on is computed using amplitudes methods that require having high point graviton amplitudes. You wouldn't be able to do it without it. There is no other state of the art. It was never done before with post-Newtonian or other methods. So it's a choice of either having that or not having it, because certain orders just have a lot of gravitons in them. And if you were doing with Feynman diagrams, well, it's impossible. You just wouldn't be able to do it. I shouldn't say it's impossible. You could do it with great work, but there's a certain simplicity to it, and it wasn't done that way. So historically, it wasn't that way. But that's one option, which is something gravitational that's observable is generally super hard to compute. That would be something more experimentally minded. For colliders, that's a much different question that's more loaded, especially when there's other methods to compute. And that I would say is more of a personal choice. So things where no one could compute by other means is the best reason to use a method. Another place where there's no other means is high loop supergravity calculations, where it's like, why would you compute it this way? Well, there isn't another way because it's too hard with all other means. So that's another example. I will say though, personally for me, I'm not really computing brings me joy, but for me, it's like I'm looking for structure. So I'm kind of hunting for something different. But at a practical level, there are some instances where there's real experimental difference between being able to compute versus not. It seems high point, but the kind of point is that these experiments are becoming precision, right? In LIGO, in these observatories, they are probing Einstein's equations at high orders. We have to know about processes secretly inside diagrams that are very high valence and graviton. But it's a good question, and one you should always examine, actually, when anyone tells you to compute something, especially your advisors. Yeah. I tell that to my students all the time. Yeah. Anyway, other questions? Yes. Yes, very good. So everything here is tree level, but loop calculations are in this way of thinking, they're fed by trees. So this method of generalized unitarity I may have alluded to before builds loops from trees. And if you don't have the trees at high enough numbers of particles, you have nothing to feed it and you have nothing to compute. Yeah. But I will say, like, for calculations, it's always gray for me because, like, someone could have some newfangled tool that's amazing, but like someone who's been doing it 20 years may just be really good with the old tools. So to be better, you have to be like a factor of 10 better than anyone in history for them to adopt. So it's generally hard, and I think that's reasonable. Like, just because something fancy works for someone who isn't used to things and isn't like hasn't been doing it for a while, like, doesn't mean it's better. But there are some things that you can't fake, like finding structure, and maybe that's a good segue to the next topic, which is hidden structure and the double copy, where it's not like there was a second way to diagnosis, but it was discovered by looking at these objects. Yeah. So if there aren't other questions, let me dive into the double copy. And it's great because we kind of lined up all our ducks and we saw we have the amplitudes. We can actually compare them and study like with mathematical precision what I mean. Um, let me let me write down the kind of schematic statement and then show you the examples using the formulas that we've already derived. Okay. The schematic statement that is often said about the double copy is gravity equals Yang-Mills squared. So GR equals Yang-Mills squared, which we already saw is an actual explicitly true formula. It's 3 particle scattering is just a fact. Like literally, those are the amplitude squared equals the other amplitude. But this actually persists to higher point. Let me tell you the lay of the land and then show you an example. A statement of this type holds and was actually discovered even in the case of string theory, something known as the KLT relations, which relate open string and closed strings, which are the kind of stringy avatars of gauge theory and gravity. Okay, so there's a very general stringy relation, which at low energies, it's a statement about graviton and gauge theory amplitudes. So that was like the real precursor of this picture. And what KLT gave was a statement relating sums of products of gluon tree amplitudes equals a graviton amplitude. Okay, so the kind of key point is it's algebraic moves, sum, product. Okay, there's no integrals, there's no extra work, and it's a formula. Okay, so in the way that we compute in GR is like we have on our computers hard coded a formula which gives us all GR amplitudes. We can always do that. There's a more modern incarnation of this, which is known as so yeah, maybe I should write this down. So there's KLT, which was the stringy version I just mentioned. This is from strings, ultimately. Okay, but there is a field theory version, which seems more general, or it somehow has a different kind of it kind of flexes in a different way, called BCJ, Bern, Carrasco, and Johansson, which I would say is sometimes considered kind of the more field theory version of this, but has more than that. It's something which apparently you can do beyond tree level into loops, as they and others and myself and others have studied. So it's a statement that persists into higher loops in a way that I'll describe, and also applies much more broadly than kind of the stringy theories like gauge and gravity. Okay, it applies to theories like the chiral Lagrangian. Okay, for instance, there's other parts of the world that happen to be described by physics that this concerns. So let me to begin. Let me just show you the leading version of what the double copy is, so you can really just get our kind of hands dirty. And then well, okay. Actually, let me start with the not even zero, like the minus first version, just to remind you of something I said a little bit ago, but maybe it'll be a little clearer from last time. When we wrote down the Yang-Mills 3-point amplitude, I had a statement where I said we had some structure constant, and then we had some momentum dependent stuff like E1, E2, P1, E3 minus P2, E3, plus cyclic. Okay, I'm not going to keep writing that, but a formula that's in your notes somewhere. And this thing in square brackets was fully antisymmetric, and F was fully antisymmetric. And I kind of intimated, like, isn't it funny you can take the constants, like the coupling constants, throw them away, and replace them with another factor of the momenta, because it was antisymmetric, and that was gravity. Okay, and that was the first version of the double copy. It was a way of thinking about structure constants as kinematic functions secretly. Okay, so like the real like deep way to understand color kinematics is to, whenever you see a picture like this, not even assume that F is numbers, but that it might be kinematics. Okay, that's the best way. That's when you've like reached nirvana. You like you know that like F is so general that maybe it's not even from a gauge theory. Maybe it's just secretly writing another factor like this, and you'll start seeing that you can take that analogy very far. Okay. Now, what is the thing you're missing? Well, you have an antisymmetric structure constant, which could be kinematics, but you don't have the Jacobi identity. Okay, that's crucial. We saw that. The Jacobi identity was crucial. Okay, let me say it this way. When we talked about Yang-Mills theory, and we talked about 4-point Yang-Mills, we derived Jacobi identity as a constraint on these Fs. Okay. Now, if that had happened, and right at the end I said, I tricked you, F was not numbers. I just tricked you. F wasn't numbers. F was more kinematics. You would be like, wait, what do you mean? Are you saying that there is a set of kinematic functions that you called F for some reason, which satisfies the Jacobi identity, okay? And the answer to that is yes, and that defines gravity. Okay, so let's do that now. So what we're going to do is take the same picture, commit to it, and go to 4-point, which is really what the kind of most primal version of this is. Oh, sorry. Before I do that, I have to take care of some. Just since we're at 3-point, I have to take care of a little business here, which is to write down a theory we haven't yet discussed, which is crucial. Okay, which had to do with committing to F. We have a GR version of this, which is E1, E2, all this junk squared, as I just said, just the same kinematic squared. This is sloppy, but hopefully you know what I mean. There's no structure constant. There's a third combination, which we haven't yet talked about, where instead of replacing F with kinematics, I replace kinematics with another F. Okay? We didn't do that, but we could have. Okay? So in particular, I could have written F A1, A2, A3, and then just put another structure constant, which I'll call F A1 bar, A2 bar, A3 bar. Okay? So these are both numbers now. Okay? They're both structure constants. This is an amplitude in a theory, which should be, maybe it should be relatively clear, like what its kind of internal symmetry structure is. Why? It has two structure constants and multiple labels for each leg. So leg 1 has an A1 label and an A1 bar label. Leg 2 is an A2 and an A2 bar label. Okay, so each external leg has two adjoint indices. Okay, for that reason, this is called bi-adjoint scalar theory. So this is bi-adjoint scalar. Let me just write the Lagrangian so that like you can ground this in like something you know. So this is d phi a bar, d phi a bar plus f ABC, f a bar, b bar, c bar, phi a bar, phi bb bar, phi cc bar. Okay. Not bifundamental. We're very used to seeing bifundamentals in like, well, the standard model in phenomenology and so on. So I'm not saying bifundamental, I really mean bi-adjoint. It has two indices that are both an adjoint of two different gauge groups, which are the A and A bar. Okay? So A is one of the adjoints, A bar is the other adjoint. And there's a cubic coupling. So it's like a phi cube theory with more structure. Okay? The 3-point vertex is just this. 3-point amplitude slash vertex is just this. Okay? So this kind of doubly colored theory is called bi-adjoint scalar. Yes. Okay. Any questions about like the definition? We'll get to the motivation. Okay. The motivation for what to define this is in some sense, all of these are secretly bi-adjoint scalar, but with interpretation for what these F's are. Okay, that's kind of the upshot. Like I said, it's actually also kinematics, and this is kinematics. This whole thing's gravity. Like, this is the kind of moves we're going to make, which is to think about a theory like this, but with momentum-dependent coupling structure constants in some sensible way. Okay, any questions? Let me mention one more thing, just because it's amusing. Sorry, I don't want to give 3-point like short shrift here. So there's one more 3-point amplitude I didn't write actually. You'll notice I actually missed a logical option. Which is the following. What if I write down this factor? Okay, let's call this E1, E2, times so on. And then put another factor of the exact same expression, but for different polarizations. Okay, which I'm going to call E1 bar, E2 bar, and so on. Okay, so like these are like a bunch of vector polarizations. These are other vector polarizations, but I'm distinguishing them. So E1 bar is not E1. Okay. In the case of gravity, again, just to remind you, this thing was quite bilinear. So it had E1 and E1. There were two E1s, and I called that E1 mu nu. Remember, the reason why there were two E1s was because I had a tensor that I split. Here, I have two different fields, E1 mu, E1 nu, E1 mu nu. Okay. But this barred field is not the same as this field. So in other words, if I thought of that this is like a tensor, some theory of a tensor field, that tensor is not symmetric. This is the amplitude for a theory that has anti-symmetric components in the tensor. Gravity is a symmetric tensor. This has anti-symmetric components, and in principle also a trace. Okay. Turns out, as is always the case in amplitudes, this you can write it down. It's consistent. It has a name. The name for it is general relativity plus a dilaton, which is the trace mode, plus an anti-symmetric two-form, which is just an anti-symmetric field with a two-form indices. So two anti-symmetric indices. This is known as the axion in 4D. Okay, so this would be like a dilaton axion pair in 4D. Okay. Maybe not coincidentally, these are precisely the low energy modes of the closed string. Okay, it's not just the graviton. There's also the dilaton and the two form. Okay. Good. So we mixed and matched and we got something new. So in fact, this is a slick way to get axion and dilaton amplitudes. Okay, with the same trick. Okay. So we fleshed out at least the main players and what's going to be the double copy. Let's see it in work. And we'll look at it for the simplest case of Yang-Mills theory, where we already have studied it to some high extent. So we have Yang-Mills 4-point. Okay, so we computed this with spinnericity. We computed, I think, we studied a bit maybe with Mandelstam's. But let me write it in the following way, okay? So I'll write down the structure, and then I'll explain why we're taking it. I've written ansatz like this before. I shouldn't call it ansatz. It's just a way to write the amplitude. When I say ansatz, it makes it sound like I had a choice or that sometimes I can't do this, but you can always do this. So go to your favorite way of computing, your favorite textbook, or maybe even an amplitudes textbook, and compute the 4-point Yang-Mills amplitude, and you will find that it has color structures, CS, CT, and CU. Okay, so CS, CT, and CU, these are different from the CST I defined last time, but they're kind of shuffled around versions of them. CS here is the summation of F, A1, A2, B, F, A3, A4, B, sum on B. And CT and CU are the other combinations of Fs. Okay, I don't want to keep writing these, but there's these three triplet of Fs where we keep permuting the indices. Okay, we cyclically clock 1, 2, and 3, and that gives us the other Fs. Okay, I'm going to call that CS, CT, and CU. The reason I'm calling them that is that these are the structure constants you get from the 3 channels. Okay, so if you glue something in the S channel, then 1, 2 are on one side and 3, 4 on the other side. If you glue in the T channel, then it's 2, 3, and 4, 1, and so on. Okay, so these are just the structure constants that show up in each channel. Okay. Everything is labeled by CS, CT, and CU. Of course, it is true that they satisfy the Jacobi identity, which is CS plus CT plus CU equals 0. Okay, which we proved at 4-point. Okay, with factorization. Okay. So that's what the C's are. C's are color factors. ST and U are just poles. NS, NT, and NU is where all the momenta, spinners, everything that's kinematic is there. Okay, so NS, NT, and NU are everything else. Okay. Now you may wonder, have I dropped a term? Because at least maybe in your minds, reasonably, you would say, well, this must be this, and it's always fine to do this. Like, what does a Feynman diagram say? This is S channel. This is T channel. Okay, and that's U channel. Where's the contact term? Yeah, like in Yang-Mills, we have this. Where'd this guy go? Okay, that's fine. That's still here. Why is it still here? This contact term can be absorbed into any of these terms, S, T, and U. In particular, let's say NS was linear, had a term that was linear in S. The S would cancel the S, and it's the contact term. So this is not, I've lost nothing by writing it this way. Contact terms can always be kind of blown up back into non-contact terms if I just multiply by S or divide by S. Okay, so said another way, terms like this, I have a choice of multiplying by S over S or T over T or U over U. It's totally freedom. Do whatever you like, it doesn't matter, but you can then write it in this form. Okay, that's all that matters you can put in this form. Okay? Any questions about that? So here the workflow is, if you really want to use Feynman diagrams, and you can do this, take your Feynman diagrams, take your S, T, and U channel to Feynman diagrams, and they're already in this form. Take your 4-point contact, and depending on its color structure, multiply by whichever factor you need, and then dump it into NS, NT, and NU. Okay? But the point here is that NS, NT, and NU all depend on, so they depend on all the kinematic stuff, like P's and E's. Okay, PI and EI, all that junk. Okay. Very good. Any questions? All right, so let's notice something fascinating. Okay, in fact, let me just tell you what it's going to be, and then we'll check it. Okay. Obviously, N and S are like partners. They're like next to each other. They look very similar. I've already hammered on Jacobi identities. So it's natural to ask about the quantity NS plus NT plus NU. Okay, the sum of the kinematic functions. Okay. Turns out this is 0. Also, this is also 0. Okay, the function of momenta and polarizations, you sum it, and if you make sure you're on shell, you have to be on shell, because if you're not on shell, nothing is physical. But for on-shell kinematics, this is also vanishing. Okay, precisely mirroring the C. Okay. Let's see how that works. Let's just do it. Okay. Let's see. Yeah. Okay. It's gonna be some equations, but maybe being explicit is better here, just because this is the first time we've seen this. So let's check this expression. So we're gonna check it in the following way. So I'll remind you of our Yang-Mills 4-point amplitude, which it's gone. So Yang-Mills 4-point amplitude in spin or helicity we wrote as angle 1, 2 squared 3, 4 squared times CST over ST plus CTU over TU plus CUS over US. Okay? And then we like solve for this thing. Okay? And recall we had CST minus CUS equaled CS, okay, what I called CS. And then I had two other equations, okay? So maybe I should just write it out. C2U minus CST equals CT, and then CUS minus CTU equals CU. Okay, remember last time I just added these three equations, and I got the Jacobi identity, okay? This is just me repeating that. Any questions? Okay. Now if we plug this in to this expression, so what we can do is, let's do it very explicitly, I guess. We can write the Yang-Mills equation of motion, not the equation, the Yang-Mills amplitude by plugging in, well, sorry, I should say it this way, by comparing this to this. Okay, so CS is equal to these expressions, so let me just plug in. So let me write this as that ansatz. What we have is that CST minus CUS times NS over S. Okay, that's just the first term, plus the other two terms. So let me write it out, CTU minus CST NT over T, and so on. Okay, there's three terms. This is me just plugging in these expressions into that ansatz. Okay, so this is just CS, CT, and then CU is in the other term. And now we just compare left-hand side and right-hand side. Okay, so I can just compare CST on both sides, CTU and CUS. Yeah, it's kind of a slick way of solving for these expressions. And what we get is a system of equations for the n's, NS, NT, and NU. Okay, which is our goal. We want to compute NS, NT, and NU, and we want to check that identity. So we have TNS minus SNT equals angle 1, 2, 3, 4 squared. Okay, that's just like plucking off the the CST coefficient. Okay? And then we have other coefficients, UNT minus TNU equals the same thing. And then a third equation. Okay, so like it's all equations that roughly look the same. And we can write the system of equations in the following way: as a matrix that acts on NS, NT, and U. This matrix looks like T minus S 0, 0 U minus T minus U 0 S. And it equals angle 1, 2 squared, 3, 4 squared times 1, 1, 1. Okay, this is a very long-winded way of solving for ns, nt, and nu. There's other probably better ways, but we can now invert this matrix to solve for ns, nt, and nu. Okay. Now, when we do this, okay, right, we want to get a solution for nst and ns plus nt plus nu. We immediately find a problem, which is that this matrix does not have an inverse. Okay, its determinant vanishes. Okay. What does that mean? That means that there is actually a zero eigenvalue of this matrix, which means there is multiple choices for ns, nt, and nu, which can give this. Okay. Now, if you think about it, it's not that surprising why that should be true. Okay. In other words, I'm saying ns, nt, and nu is not unique. That should be clear based on what I said about that quartic. You can slop that quartic around. That's a freedom. There's just a freedom. There's not a unique way of writing this. You can do it a million ways, corresponding to the way that you kind of repinch and move that guy around. So we never should expect ns, nt, and nu to be unique. And there should be a freedom. So let's solve for this, but include that extra freedom. What do we find? We find the following solutions, which includes a kind of additional free parameter, which is unfixed, which is the following. ns equals minus 1, 2 squared, 3, 4 squared over u plus nu s over t, nu s over u, and nt is equal to angle 1, 2 squared, 3, 4 squared over u plus nu t over u. Okay, what was the freedom? The freedom was nu, okay? Nu is unspecified. Nu can be anything you want. Okay, you have an entire function's worth of freedom, which makes sense, because this is a very broad ansatz. Okay? But this is the solution. For any choice of nu, ns and nt are these expressions. And you can immediately see that if I sum them, ns plus nt plus nu, okay, this term cancels, these terms add, but s plus t is minus u, so I get precisely 0. Okay. So in terms of our spinor helicity expressions, we've found that ns plus nt plus n equals 0. Spinor helicity wasn't necessary, by the way. We can do this in general dimension. I could leave this as an exercise. Take the Yang-Mills 4-point amplitude with polarization vectors, like in Peskin. Put in that form, okay? And then just write this expression, ns plus nt plus nu, whatever choice you make. Right. My claim is, if you evaluate that on shell, which means going to a minimal kinematic basis, that means eliminating P4, all that junk we did before. Eliminate all the redundant and unnecessary P.Es and P.Ps, get rid of them. What you'll find is it also vanishes, okay? So this is a general dimensional statement, okay? In Amplitudes land, this is called the kinematic Jacobi identity. Kinematic Jacobi. To be contrasted with the color Jacobi identity. Okay? Now, again, depending on, if you know enough about field theory, this should seem crazy to you. What is this? What's going on here? This is momenta. Momenta are satisfying a Jacobi identity. There's no matrices here. There's no Lie algebra. There's nothing here. What is causing this to be true? Yeah, that's already puzzling. Here's what is kind of more amazing, at least in my view. This is the real leap of B, C, and J. Well, they saw this feature and they said, well, NS, NT, NU, they're just like CS, CT, and CU. They're exactly the same. These are on totally equal footing. Okay? In fact, when we check the Yang-Mills 4-point, we determine Jacobi identity as a consistency condition. So what that means that, I kind of joked before, if those FABCs were secretly kinematic, it seems like Jacobi would be implied by them, and indeed it is. And it suggests that we should really interpret CS, CT, and CU either as color structure constants or as kinematic structure constants. So these will sometimes, people talk about these as products of kinematic structure constants in the same C as products of color structure constants. It's all by analogy. No one knows what these structure constants are. But it tells you that there is a very natural thing to write down, which says to take CS, CT, and CU and replace them with NS, NT, and NU. Okay, giving you a new object, NS squared over S plus nt squared over t plus nu squared over u. Okay, what is this new object? So this object has no color. Okay, like the first step in color kinematics is always the same. Take the color structure and just throw it away. Just like throw it totally in the trash. So often I'm asked, like, does color kinematics work for SUN or SON? Like, it doesn't matter. Step one, take the color group, throw it away. I don't care what it is. Then replace it with kinematics. Okay, notice there's no C's here anymore. I didn't matter what CTC was. I dropped it at step 0. You're left with something that has no color, no other labels other than kinematics, and where the numerators have been squared. Okay, now the numerators are where the momenta are, so the momenta has increased. The number of momenta per vertex has increased. Turns out that this is exactly the GR vertex. Okay, so that's the magic. You could probably anticipate, given what we're saying. This is the general relativity amplitude, the one that takes a lot of work to compute with Feynman diagrams, which is easy through a bootstrap in 4D, but in general D it's very hard. Okay, so for computing this in general dimensions is a nightmare, as I've said, but this is super fast to compute. Okay, and obviously the maximally simple way to write it. Okay. Now you can do other moves. Okay, so this is one thing you could do. You could do a different thing. Okay, which is let me take CS. Let me take NS and replace it with CS. Okay, so I replace it with another factor of CS, CS squared over S, plus CT squared over T, plus CU squared over U. Okay, so in other words, I dropped the kinematics, and now it's all coupling constants, but squared. This has a name too. This is exactly the biadjoint scalar theory we saw before. Okay, at 4-point. These are all 4-point amplitudes. Okay. In other words, this thing here is just this exchange diagram where this is a cubic scalar interaction, and since everything is a biadjoint, there's 2 of them. Okay. There's a third thing we can do, which is okay. I guess I'll write it down here. So there's yet another thing we can do, which is we can take NS and NS bar over S, where NS bar means take those polarizations and send them to tilde polarizations. I guess it's erased now. But at 3-point, I was playing this game where I took some polarizations and I barred them, right? I can do the same thing here. Okay, NS has some gauge boson polarizations. So NS has some gauge boson polarizations. NS bar is the same function, but with the bar on the epsilon. That's all it is. The polarizations have a bar. This thing, as you can all certainly anticipate, is the amplitudes in axion, dilaton, general relativity. So the same, the thing we saw at 3-point, yet again. And U bar over U. Okay. So these are all theories. The reason why this should maybe surprise you the most, I would say, is that you don't get to like just square terms and still have gauge invariant sensible things, right? Like this should be obvious, but like if I have a fully gauge invariant object and I square it, like a full amplitude squared is invariant because the full amplitude is invariant. But I didn't just square the amplitude. I like went term by term and squared each one, keeping the poles. Okay, so this is not a triviality that the final answer is even consistent. Okay, it's like kind of a miracle that it's still consistent. Okay. Let's see the specific example of GR, the GR case. I mean, let's just really plug in. Okay, so in fact, we have NS and T. So let's just doubly check that we get the graviton amplitude because we can compute it. Okay, so what is GR? What is AGR? So A for GR is just N squared, NS squared over S. So NS squared over S plus NT squared over T plus NU squared over U, which you can rationalize and write it in the following way. Angle 1, 2 to the 4th, 3, 4 to the 4th plus T. So just put everything under one giant denominator by plugging these into that expression, and you find the following: ST times S plus T plus U over STU. There's actually a minus sign here. Okay. But okay, all I'm saying is take NS and NT and just plug it into that expression with the squared numerators, and this is what you get. And incredibly, this term here goes to 0 because S plus T plus U is 0. Exactly the term with that freedom of NU. This S plus T cancels U, and we get our known expression. Sorry, there's a square here. Yeah. So it cancels one of the u's, and we get this over STU. Okay, so it's exactly the amplitude we had before. Okay. Again, it's a bunch of algebra. You want to see the algebra, you should look at the TASI notes. Any questions about that? Okay, great. So what we've learned is that the two completely rigidly fixed theories, fixed by Lorentz invariance, are not just rigidly fixed and immutable and unchangeable. They're also directly related by something which suggests the existence of a kinematic symmetry, a kinematic algebra. Okay. So this all holds at 4-point in this example, and it generalizes to any number of particles. Let me show you like what the structure of that is. You have a question? Yeah. Good. So when you say something is a square of something, I'm not sure if you're being schematic or exactly mathematically correct. I would say at a mathematical level, AGR is not the square of A Yang-Mills. It's not the literal square. If it was a literal square, it would be a problem because if I just squared A Yang-Mills, I would get a double pole in S, double pole in T, and a double pole in U, and cross terms. Okay, it would be a mess. This is not the perfect square. I mean, this is not the square of this. It's something more subtle. It's the square of the numerators. So when people say the words double copy, they're saying square the numerators, at least in this context. Or take products of numerators, okay? Actually, maybe it's worth even, yeah, actually. Actually, before I go up to higher point, let me mention the other double copies, which I didn't even get to, but I should. Okay. So you could say, okay, this is a moderately big ecosystem, gravity, GR, axions, zilitons. Let me throw pions in too, okay? So you can do the same thing for pions, okay? Let me just show it to you, okay? So, and here's what's crucial. Here's what's the most fascinating thing about this construction. The rules never change. I'm gonna do the exact same thing for pions, and we're gonna get a whole bunch of new theories, and I'm gonna take products of Yang-Mills and pions. Okay, so we'll do that next. But it's the same formula, so it's not that big a difference. Okay. We haven't talked about pions because it was normally something I would go through, but we kind of don't have enough time. But that's okay. Like, let me just show you the chiral Lagrangian amplitudes, and then we'll just use it. Okay. Maybe before saying that, let me again just at the I don't want to risk being unclear. I'm going to talk about amplitudes in the NLSM, just so we're on the same page. By this I mean the Lagrangian that describes the low energy degrees of freedom and the strong interactions after chiral symmetry breaking. So the usual picture here is that we have some matrix, some unitary matrix U, which is some e to the I pi over f pi. Hopefully you've seen this in your QFT textbooks. Pi is some matrix valued pion, and we can just compute amplitudes in this theory. Okay, the pions are like any other degree of freedom. We can compute the 4 pion, 6 pion, whatever are pion amplitudes. Super duper explicitly, this thing looks like d pi squared, and then it has d pi, 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 and then d pi, 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 like 4 pi's, and so on. Okay, and there's all this like trace structure. Okay, and there's like a complicated trace structure you have to keep in mind. Okay, now this maybe isn't this is well known in amplitudes, but maybe pions are a great like toy model of Yang-Mills because it has a lot of the same kind of structural properties. Okay, Yang-Mills has color. Okay, pions have flavor. Okay, there's a flavor structure. Okay, there's a trace, there's products, and at least for technical reasons, for the case of a symmetric Gmod H coset space, you can write all the pion amplitudes in terms of structure constants. Okay, you don't have to know the reason why that is, but it's just true. When you write down pion amplitudes, all the flavor structures, if you have a Gmod H coset, can be expressed as structure constants of that manifold. Okay. In the end, what you get is amplitudes that look exactly like this, except CS, CT, and CU are flavor structures. And the structure constants satisfy Jacobi and so on. Okay? You can take that. I'm happy to explain it to you more if you are interested afterwards, but it's just a fact about symmetric coset spaces. But the point is, NLSM is the same form. Okay, so A4 NLSM you can compute, and this I mean like like 2 pions come in, 2 pions come out, and it's precisely the same structure as that. So, in fact, let me start labeling it so. So CS NS NLSM over S plus CT NT NLSM. Okay, I really have to start saying what theory we're talking about because we're going to mix and match a lot of theories. NLSM, sorry, NCU over U. Okay, where CS, CT, and CU, I'm still calling C, which normally I think of as color. It's an abusive notation, but common usage. It's secretly flavor. Okay, it's all the matrices. It's numbers. It's not momentum. That's the key point. Okay, any questions about what this means? Maybe also to hammer this down, let me call this Yang Mills, Yang Mills, Yang Mills. Okay? Just because I'm going to start, as you can imagine, start messing around with these. Okay. So that's NLSM. In fact, let me just tell you what it is. So you could compute this any way you like again, but let me just tell you what NS, NT, and NU are. So this is minus S squared, NT, NLSM is S squared minus U squared. Okay, again, this is a choice. There's always freedom, but I'm making a nice choice. NU, NLSM is U squared. Okay, so the point is you just plug these expressions in, and you'll find a bunch of flavor structures. The thing that should bother you probably right at the start, once I wrote this, was the poles. Okay, S, T, and U. If you know even a little bit about the Chiral-Lagrangian, even just what I just wrote here, that should be confusing, because the Chiral-Lagrangian has no odd point at vertices. It doesn't have a cubic interaction. It's got quartic, got 6 point, and so on. It has no cubic. Okay, so you're like, wait a minute, why is this guy writing down poles here? Don't worry, all the poles get canceled. Okay, as usual. It's just like the quartic and Yang Mills, which also shouldn't make us afraid. We're just choosing to organize it with these denominators. Okay, so everywhere you see a pole, it's not physical; it will cancel. Okay? You can even check it yourself. Okay, so when you plug all these in, you'll find that every single pole cancels by construction. Why do we include them? We include them so we don't have to change the rules. And in fact, the rules shouldn't be changed. We'll see that something beautiful happens here. Okay. Let me. So first of all, you see already, this satisfies the Jacobi identity. NS plus NT plus NU is 0. All the S's and U's cancel. Okay. Whoa. Wow. Okay. Weird. Chiral-Lagrangian. Another theory, random theories, describes pions in the chiral limit, also satisfies the Jacobi identity. Well, we know what to do at this point. We have a workflow. We are just going to square this thing and see what pops out. So let's do that. So what do? We take NS, NLSM, and square it and divide by S. So double copy the numerators. And then NS and NT, NLSM squared over T, and then NU, NLSM squared over U. Okay, so a bunch of algebra that isn't important. Okay, you just plug in, expand, and you get minus STU. Okay, so what is this? This is something which goes as p to the 6th. Actually, is an amplitude that has showed up before, and in a theory that has a name called the Galilean. Okay, so if you don't know what the Galilean, it's okay. I mean, it has lineage connected, I think, with many institutions in Italy. But the Galilean is a beautiful scalar theory with a really big shift symmetry. Okay, let me just write down what it looks like schematically. So this is Galilean, that's what this means. The Lagrangian for the Galilean schematically looks like the following. It's a single scalar. Okay, so this pi was a multiplet. This pi was a matrix. It has some flavor. Galilean has no flavor. It's just one simple scalar, like a bleached single scalar, real scalar. But it has an amazing shift symmetry where its interactions look like d phi to some power times d phi squared. Okay, so it has a lot of derivatives. It's a lot of derivatives. It's terms like this, a huge number of derivatives, but it has a really nice shift symmetry, where if you send phi goes to phi plus a plus b mu x mu, and in some cases even higher order, it's invariant. Okay, so maybe you've had this question in your life before, but you know that if you write down a theory that's invariant just under the first shift, that's called a Goldstone boson, right? Something invariant under shifts of phi just is a Lagrangian that depends on d phi. This goes to the next level. It says, well, what if it's invariant not just under shift, but under any additional shift that's proportional to x mu position? And this is that Lagrangian. Despite its name, it is totally Lorentz invariant. It's like a historical, because this looks like a Galilean symmetry, that it's called the Galilean, but it's a totally Lorentz invariant theory. We haven't left the world of Lorentz invariance. It's just a name. But this is that Lagrangian, and this is its amplitude. Okay, so the statement is that gravity is Yang-Mills squared. A new statement is that the Galilean is pion squared. Okay? It's already enticing that these things are all in hep-pH and hep-TH for like totally different reasons. I mean, Galilean studied as an interesting modification of gravity, but also as like a toy model for gravity. It turns out to be, it's well known mainly as the longitudinal mode for a massive graviton. So for folks who think about modified gravity, if you want to give the graviton a mass, it's very similar to giving a gauge boson a mass, right? So if I give you the photon a mass, it gets a longitudinal mode, right? It gets an additional degree of freedom. You can think of that degree of freedom in some limit as being its own interacting theory. Similarly, for gravity, if you give the graviton a mass, it's got many additional modes, but one of them is this Galilean mode. So it kind of plucks out like the most strange part of the massive graviton multiplet. Okay? So that's its whole backstory. Studying cosmology and all sorts of things has issues likely with causality, and it's not clear it's a consistent theory. In fact, I think maybe most think it isn't. I think rightly, but it has shown up here. Okay, very good. Any questions about that? All right, one, yes. Yeah, yeah. Yeah. So they're both scalars on both sides. So crucially, in terms of little group, which is kinematics, it's scalar and scalar. Okay. The thing they differ in is their multiplicity, is in their flavor structure, but that was precisely the CSC-TCU that we threw out. So that's the thing, they exactly match. They're scalars on both sides. Even though this has flavor and internal structure, it's precisely the thing we throw out immediately to get that. So we killed it. So we took the flavor group, the G mod H. You could be like, G mod H did this work for? It doesn't matter. I took them, threw it out at step 0. Just like I threw out the gauge group for Yang-Mills at step 0. Now we can do something, let me do this last demented thing, which is, this is really demented. Because these, you could be like, okay, pions is Galileans, weird, okay, not that weird, still weird. Yang-Mills squared is gravity, that's weird. Okay, let's take the two sides and glue them together across, okay? So I'm gonna take Yang-Mills and pions. Let's glue them together. Okay, they're different spin and different universes, okay? What are we gonna get? Well, so let me use this as a shortcut for writing things over. So I'm gonna take the C's here, okay? And I'm gonna replace them with NLSM. Like, so I take NS, NLSM. Okay, so NT, NLSM. NU, NLSM. Okay, so this is this is like an asymmetric product. I'm taking a theory and I'm making one side Yang-Mills theory, and I'm taking the other side and I'm making it pions. Okay, so these are truly like not supposed to be together in the same conversation. Like, no, you shouldn't be saying gluons and pions in the same place. Definitely not gravitons also, which are also going to come into play, but they're all connected. And this is another theory. Okay, let's see what that theory is. Okay, so this actually plays more interestingly because Yang-Mills has spin, pions have no spin. Okay, so it's a scalar and a vector. Okay, just by little group, I know this is a theory of a vector. okay, because the spins add, as we've seen. So scalar and vector together is a vector. There's no color or flavor. It's removed, right? The whole point was I removed all the color, flavor, structure. So this is some theory of a vector that is somehow got more derivatives than usual. Okay, that's what it is. Well, in fact, let me save you time. You plug in all the expressions we had, and you get the following expression: angle 1, 2 squared, 3, 4 squared. Okay. And the amplitude that this is in something called Born-Infeld theory. Okay, so Born-Infeld theory, again, this is like theory had a name before this all showed up. Born and Infeld, these are the classic things, clearly. It was a nonlinear deformation of Maxwell's theory. Okay, so a UV completion of Maxwell, not UV complete, but a deformation of Maxwell's theory that has really nice properties. So if you haven't seen this, it's a very cool theory, Born-Infeld. The Lagrangian looks really kind of crazy. It looks like something like determinant of eta mu nu minus F mu nu, or plus F mu nu, where F mu nu is the field strength, like a linearized field strength of a photon divided by some scales, like lambda squared. Okay, so F mu nu is like really like d mu a nu. So F mu nu is d mu a nu. It's a linearized Maxwell field strength. Ooh, oh wow, I've destroyed this like priceless tradition in so many ways. This is a metaphor for, yeah. Anyways, this is just the Maxwell field strength, and it's put in a determinant, and it's under a square root. Okay, where does this show up? So this was observed that it very nicely kind of screens point-like singularities in Maxwell theory. That's why it was conceived. All the time in like cosmological context. So there's a scalar version of this, which is sometimes discussed, which represents the motion of a brane, like a motion of a 5-dimensional surface on which we live, accelerating in some 5th dimension, called dBi. Okay, people use this for inflation. People study this in string theory. Okay, it has a name, and it has popped out here. Okay. Now, of course, you could ask me, wait, how do I know this is the theory? This has really high order pieces I haven't probed. Of course, the back of my mind here, this all holds at endpoint. And when you go to endpoint, you see that these are all the theories. Okay. So the full multiplication table is the following. Okay, so we can now do an accounting of everything. And this is like a baby version, maybe. So how should I probably stop pretty soon? Yeah. So let me. Yeah. Let's wrap it up. Let's. You gotta play the music to have me finish this speech. So just right at the end here, let me summarize the multiplication table. Okay, this is the multiplication of the most basic multiplication table of theories. Okay, which is we could have Yang-Mills, we could have NLSM, Yang-Mills, NLSM. Okay, but we also have biadjoint scalar theory. Okay, so this is actually, biadjoint scalar theory is like the identity in terms of multiplication tables here, for reasons that you'll see. So when I write this multiplication table, I mean the following. I mean, take the structure constant and replace it with the relevant quantity in that theory. Okay, so when I take biadjoint scalar theory and biadjoint scalar theory, I'm just saying like take those two f's and make them both the f's of biadjoint scalar theory. So this is just biadjoint scalar theory. Okay. Now if I take both that one f, if I take one side and I make it Yang-Mills and make the other side Yang-Mills, I get GR. Okay. If I take NLSM and NLSM, I get the Galilean. I get Born-Infeld here, Born-Infeld. And then everything else is the identity. So this is also Yang-Mills, this is NLSM. So if you like, it's a little formal, but biadjoint scalar's job is to just like do nothing, essentially. It says remove your color and replace it with color. It does nothing. Like I stripped off that color and I replaced it with another color. That's why it does nothing. So that's why these are trivial. Okay. Okay. This is just one part of a giant table. Okay, so if you want to see the bigger version of this, you can look at an awesome review by Zvi Byrne, Radu Roybon, J.J. Carrasco, Henrik Johansson, like the creators of many of these ideas, most of these ideas, the inception of all these ideas, with a big table of theories, like theory A times theory B equals theory C. This is a small subset of them. They also have theories like supergravities, of course, with n equals to 0, 1, 2, 4. They have theories with matter, QCD. Higgs phase gauge theories, conformal gravity, Goldstino. Oh, I didn't even mention that. You can take the gauginos of a supersymmetric theory and multiply them against pions, and you get Goldstinos. It's insanity. You get the Volko-Akolov effective field theory of Goldstinos. Okay, lots of other theories, and they all are consistent. And we have no idea why. I'll talk about why next lecture. Maybe I'll stop there. Yeah, thanks.